astronomy was formerly an endeavor to seek illumination. Humans have scrutinized the night sky for millennia, striving to understand the essence of the cosmos we occupy. Due to the constraints of human vision, most of our predecessors were unaware, and none comprehended, that the stars were other suns and the planets were other worlds. Such disclosures were contingent upon the advent of the telescope, a device that enabled and realized the potential to observe fainter and more distant celestial objects. Although the early telescopes had limited functionality akin to contemporary toy telescopes, they nonetheless unveiled, for the first time, the moons of Jupiter, the craters on our moon, and the multitude of fainter stars within the Milky Way. With the advancement of telescopic power, it was presumed that telescopes, as instruments for collecting light, would uncover increasingly more of the surrounding universe, and ultimately disclose all its secrets. Modern telescopes have captured photos of objects so far that they approach the boundaries of the universe and the limits of physical detectability. Without the light-gathering power of telescopes, our comprehension of the universe may have remained limited to the Milky Way, regardless of the interpretations derived from their observations. The initial genuinely modern telescopes, constructed on elevated mountains in the early decades of the 20th century, established the foundation for our narrative. Seated in their lofty ivory towers, astronomers discovered themselves, literally and metaphorically, nearer to the stars than ever before. These were exhilarating times for astronomers. Our insular perspective of the universe, whereby the Milky Way was the predominant feature, broadened to one in which our galaxy assumed a subordinate position. Stars congregated into galaxies, and galaxies amalgamated into clusters of galaxies. The universal expansion was independently and concurrently identified and elucidated, leading to an inseparable collaboration between astronomy and physics. Astronomers sought physical explanations for their observations, while physicists recognized the universe as a vast laboratory of significant scale and energy. Regardless of the philosophical implications of these discoveries, or possibly due to them, the future of astronomy appeared promising. Astronomers observed the night aglow with the radiance of countless stars at practically unimaginable distances. However, in every direction, astronomers observed, a certain element was absent. The stars and galaxies shimmered in the night sky, resembling moonlight on an ocean. However, their behavior was anomalous. Instead of clustering together in the frigid void of space, solely governed by their own gravity, the stars and galaxies appeared to be influenced by enigmatic, unseen forces that seemed to pervade the cosmos. The stars and galaxies, rather than governing the universe, functioned as simple fragments of a cosmic ocean. The issue is straightforward to comprehend, yet challenging to resolve. The sole interpretation of gravity is the presence of matter. All entities in the universe exert a gravitational force on one another, a phenomenon that unifies solar systems, star clusters, and galaxies. The motions of stars and galaxies indicated the presence of more matter than previously estimated. However, when astronomers attempted to identify the origin of the gravitational force, they discovered none. As larger telescopes explored deeper into space, they uncovered structures on progressively grander scales. Yet each observation demonstrated the same enigmatic gravitational effects. The wider the scale, from stars to galaxies to galaxy clusters, the more pronounced the mystery effect appeared. The more astronomers observed, the less of the universe they perceived. The term missing mass was previously used to describe unseen matter due to its invisibility. However, this designation is inaccurate, as its location is fully established, allowing astronomers to direct their telescopes towards it. Despite the utilization of the greatest and most powerful telescopes, it remains imperceptible against the void of space. thereby earning the designation dark matter. Nonetheless, this terminology diminishes the importance of the concept it signifies. The enigma of dark matter has transitioned from an unresolved astronomical issue to one of the key cosmological inquiries. Due to the unknown composition of dark matter, which surpasses visible matter by a factor of 100. Is this only a constraint of our observational methods of the universe? Possibly. However, it is important to note that when dark matter was first identified, scientists were restricted to optical instruments, observing the universe solely in visible light. Over the past 70 years, the universe has been examined at several wavelengths, uncovering new types of undetectable stuff, such as interstellar gas and dust, neutron stars, radio galaxies, and black holes. Nevertheless, including these hitherto unidentified matter sources does not entirely elucidate the influence of dark matter. We have been searching for the incorrect issue all this time. Dark matter denotes non-luminous matter that does not emit light. What if it is composed of non-baryonic matter, the unfamiliar entities distinct from the protons and neutrons that constitute stars and planets? We must investigate non-baryonic matter, unidentified exotic particles. The composition of the universe may differ substantially from our own. This transformation in our thought processes would not be without precedent. 4 centuries ago, the Copernican revolution removed the Earth from the center of the universe. David Schramm has observed that we might be undergoing a profound Copernican revolution, as we are neither at the center of the universe nor composed of the same material as the majority. Many contenders are competing for the designation of dark matter. Neutron stars, primordial black holes, deceased stars, neutrinos, and a diverse array of exotic particles known as WIMPs. We will examine these and more candidates to observe how scientists endeavor to identify them. Nevertheless, we must exercise caution regarding the conclusions we reach about the characteristics of dark matter. Astronomers, as imaginative narrators, can formulate a hypothesis based on the available data. The scarcity of data facilitates the alignment of the theory. As astronomers strive for a comprehensive understanding of an astronomical issue, it is essential to apply Occam's razor. The simplest and typically most elegant explanation should be favored. Regarding dark matter, it is preferable to postulate a singular type of dark matter to explain the gravitational phenomena observed at both galactic and extragalactic scales. Nevertheless, the progression of our narrative indicates that the circumstances are more complex than they appear. We may need to adapt to the existence of various types of dark matter, each contributing to the gravitational effects observed at different scales. Irrespective of its nature, dark matter undeniably played a role in the universe's inception. In its absence, the universe would lack galaxies, stars, and potentially any beings to ponder the reason why. Nevertheless, it possesses them, and here we stand. Analogous to its crucial function in the universe's inception, dark matter may significantly influence the cosmic tension between the universe's expansion and its self-gravitation. The universe's expansion, signifying the Big Bang, the primordial fireball that initiated the universe, was uncovered concurrently with the finding of dark matter. This expansion is contending with the gravitational attraction of the matter it encompasses. If the universe possesses little mass, it will perpetually expand. Conversely, if it contains too much mass, it will ultimately collapse inward. Between these two extremes lies an optimal equilibrium of gravity and expansion, a critical density adequate to halt the universe's expansion in an infinitely remote future. The entirety of observable matter in the universe constitutes but a minuscule portion of the critical density. Could dark matter be the determining factor? Is the universe governed by an even more peculiar force, such as the energy generated by the vacuum of space? which compels the universe to perpetually expand despite the formidable attraction of dark matter. If accurate, then the majority of the universe is indeed dark. It is ironic that as telescopes increased in size and their detectors became more sensitive and expansive in spectral range, they unveiled not a universe abundant in light, but one enveloped in darkness. Not a universe governed by luminous stars and galaxies, but one dominated by an unseen, yet unidentified substance. The stars and galaxies may glimmer like gems. However, this brilliance is only evident against the velvety obscurity of dark matter. Despite their telescopes, detectors, and early reservations, astronomers are compelled to consider a predominantly invisible universe. They persist in examining dark matter via telescopes, laboratories, and theoretical frameworks. This rigorous search demands the efforts of some of the most brilliant minds in history and consumes significant portions of valuable observation time on the world's most powerful telescopes. It appears peculiar to employ telescopes in the quest for an invisible entity that radiates no light. Nonetheless, as these inquiries unveiled the outside constituents of our solar system, the quest for dark matter will ultimately disclose the remainder of the universe. Initially, it may have commenced as a pursuit of illumination. Nevertheless, astronomy has evolved into an exploration of obscurity. Dark matter predominates throughout the universe. Astronomers have identified more forms of matter by examining the motion of galaxies and stars. The researchers discovered that dark matter is significantly more prevalent than light matter by a factor of hundreds. Researchers must take prudence when asserting that dark matter appears to predominate, as scientific evidence is never conclusive. Nevertheless, the evidence supporting the existence of dark matter is compelling. Astronomers may now examine the universe's multifaceted occurrences more precisely due to enhanced methodologies. They may now observe the motions of objects that are diminishing in size. Time is systematically quantified on scales ranging from minute fractions of a second to the vast expanse of the universe's age. We have examined the observable cosmos throughout nearly the complete electromagnetic spectrum, consistently uncovering evidence of dark matter. What evidence indicates the existence of dark matter, particularly in such substantial amounts? The solution is the discrepancy between the universe's mass assessments, luminous and gravitational mass. A discrepancy exists between the aggregate mass of observable bright stars and galaxies and the mass suggested by their spatial motion, indicating the presence of an unseen gravitational mass. The ideas of luminous mass and gravitational mass are fundamental to the dark matter narrative. So we begin by examining how astronomers quantify the universe. A new spectrum of gravitational waves, ripples in space-time, may soon be available for investigation. Methods for determining galaxy mass. Astronomers mostly utilize the motion of stars or galaxies to ascertain a system's mass, and then compare that motion with the gravitational force required to maintain the system's cohesion. Newton initially demonstrated that the aggregation of diverse forces might elucidate the motion of objects. The resultant motion is the aggregate impact of the several forces acting simultaneously. In the context of gravity, we possess a law that exemplifies the essence of physical laws. Newton's concepts are universally applicable throughout the universe. The equilibrium between motion and gravity is frequently evident and aesthetically pleasing, best conceptualized through Newtonian principles of force balance. We are encircled by remarkable instances, such as the Moon, which orbits the Earth with mathematical precision due to the gravitational force between the two bodies, nearly perfectly counterbalancing the Moon's inclination to maintain a linear trajectory. The many particles constituting Saturn's rings are remarkable. The rings exhibit such perfect symmetry that one would question why the particles do not orbit the planet, like a halo of moths around a street lamp. Why do they not merely ascend into space or descend towards the planet? The resolution is that several original particles that likely encircled Saturn either dispersed into space or integrated into the planet. But this occurred a considerable time ago. What we observe today consists solely of those particles ensnared in a fragile equilibrium between the forces of motion and gravitation. This identical equilibrium is manifested in the aggregation of asteroids inside the asteroid belt and the spiral arrangement of stars and gas in the Milky Way. Newtonian gravitation and discovering the invisible. Although Newton's gravitational ideas face criticism as mere approximations, we should not underestimate their significance. They have proven sufficiently successful in uncovering previously undetected masses at multiple scales. The initial encounter with dark matter transpired in the outer solar system. Although Newton's rules effectively described the motions of most known planets, they appeared inadequate for the seventh planet, Uranus, whose unpredictable movements did not conform to Newtonian gravity. Regardless of the several methods employed by celestial mechanicians to adjust the calculations, Uranus consistently deviated from its anticipated trajectory among the stars. A problem occurred. Could Newton's law of gravitation possess a finite range, resulting in its failure beyond a specific distance from the Sun, thereby permitting planets to traverse freely over the celestial expanse? This may be an exaggeration, as the discrepancy between Uranus's observed position and its anticipated position was comparable to the width of a human hair viewed from a distance of 100 meters. However, this minuscule quantity exasperated the astronomers of that era more than anything else. What was the source of the error? Two talented young guys with a penchant for mathematics emerged. One individual was British, John Couch Adams. The other was French, Urbain Jean-Joseph Leverrier. By the early 1830s, the issue of Uranus's irregular movements had become so evident that astronomers speculated the existence of an additional planet located farther from the Sun. A planet of this nature would exert a gravitational influence on Uranus, displacing it from its anticipated position. Adams was the first to precisely calculate the undiscovered planet's mass, its distance from the Sun, and its position in the celestial sphere. By October 1843, Adams had developed a plausible estimate of the new planet's location in the sky. However, due to trivial snobbery and personal conflicts, he was unable to engage the interest of the Astronomer Royal, George Biddle Airy, resulting in his predictions remaining unverified. 2 years later, Leverrier conducted computations analogous to Adams's across the English Channel, completely oblivious to the prior findings. Leverrier finalized his research on September 18, 1846, and transmitted the findings to the German astronomer Johann Gottfried Galle. Galle obtained a new collection of star charts depicting the region of the sky that encompassed the anticipated location of the new planet. He commenced his search for the new planet and discovered it merely a few days later, on September 23, 1846, within 1 degree of the location forecasted by Leverrier. The finding of the newly named planet Neptune was a matter of significant contention. James Challis, Airy's successor as professor of astronomy at Cambridge, asserted that he had discovered Neptune during his own investigations, but lacked the time to confirm his finding, whereas Galle was the first to definitively identify Neptune using a telescope. Ultimately, history has attributed joint credit to Adams and Leverrier, despite Adams receiving minimal attention during his contemporaneous period. David Blair and Jeff McNamara published this report in Ripples on a Cosmic Sea. The inquiry culminated in a significant victory for Newton's gravitational theory, as the laws of gravity accounted for even the minutest anomalies. Gravitation was universal, allowing the examination of the movements of distant and enormous objects to investigate the distribution of matter in the broader universe. Nevertheless, progress in comprehending the universe at increasingly vast scales required a credible theory of gravity and enhanced observational methodologies. Quantifying the movements of stars is a significantly greater challenge than assessing the motions of planets, primarily due to the considerable distance of stars from Earth. While driving on the freeway, you may have seen that the scenery nearby shifts about your position. Irrespective of your velocity, the woods and hills progress slowly as you look toward the horizon. This phenomenon is termed perspective, and it culminates in the sky. Despite the Moon's 3,500 km/h velocity, one must observe it for several minutes to perceive significant movement against the background stars. The planets appear stationary at night, requiring days, weeks, or months to shift by even a few degrees. Measuring the movements of stars is vital for studying substance distribution among them. Nonetheless, perspective implies that even the slightest displacement of a star may need years to quantify. Nevertheless, astronomers accomplished it in a rather clever manner. Methods for quantifying stellar motions. The trajectory of a star in space is characterized by 3 dimensions. One dimension is along the line of sight, while the other 2 are within the plane of the sky. The speed of a star along the line of sight is determined by a method known as spectroscopy. When starlight, originating from a singular star or a galaxy, is transmitted via a glass prism or analogous apparatus, the light is dispersed and separated into its constituent colors. A similar phenomenon occurs when sunlight traverses rain, resulting in the formation of a rainbow. The array of vivid hues, violet, blue, green, yellow, orange, and red, is termed a spectrum. When a star emits its spectrum sufficiently, it discloses a sequence of black lines akin to a barcode. Each spectral line denotes a particular chemical element in the star and occupies a distinct, predetermined place within the spectrum. Astronomers can ascertain a star's composition by analyzing its spectral lines. Light consists of electromagnetic waves, with each color corresponding to a distinct wavelength, defined as the distance between the peaks of 2 waves. The position of a spectral line is delineated by wavelength. Lines with shorter wavelengths are situated nearer to the blue end of the spectrum, while those with longer wavelengths are positioned closer to the red end. The crucial aspect of this narrative is that the movement of a star along the observer's line of sight results in a variation of the apparent wavelengths of light. The alteration, which may manifest as either an increase or a decrease in wavelength contingent upon the direction of motion, is attributable to the Doppler effect, the identical phenomenon responsible for the variation in pitch of a police car's siren as it approaches and subsequently recedes from you while driving on the motorway. As the police car approaches, the sound waves of the siren are compressed, resulting in a greater pitch. Conversely, when it moves away, the waves are elongated, producing a lower pitch. The Doppler effect is also applicable to starlight. The star will compress its light waves as it nears you, causing any spectral lines to have a shorter wavelength. This induces a shift toward the blue end of the spectrum. Conversely, a star receding from you will elongate its light waves and displace its spectral lines into the red spectrum. The blue or red shift of a star's spectral lines indicates whether the star is moving towards or away from you, respectively. Nevertheless, we can advance the concept further. The spectral lines shift by the star's velocity of approach or recession. The line of sight velocity of a star, commonly referred to as its radial velocity, can be estimated with exceptional precision by examining the position of the spectral lines within the visible spectrum. During the 1920s and 1930s, photography techniques produced exceptionally high accuracy. Stars traverse the Milky Way at speeds reaching several hundred kilometers per second, and astronomers can measure these velocities with an accuracy of 1 to 2 kilometers per second. It is essential to recognize that determining the mass of a galaxy or galaxy cluster is a statistical process. Hence, observing a greater number of stars or galaxies enhances accuracy. Contemporary astronomers significantly enhanced the measurement of stellar and galactic velocities using optical fibers in the latter decades of the 20th century. These techniques enable the simultaneous measurement of several things. However, it is important to note that the pioneers of the dark matter frontier were limited to measuring the velocity of individual stars or galaxies, employing smaller telescopes and less sensitive detectors. The analysis of a star's motion, its radial movement, toward or away from us, constitutes merely a portion of the complete narrative. To ascertain a star's genuine travel through space, it is essential to evaluate its motion along our line of sight, within the plane of the sky. This lateral motion is the star's proper motion, quantified in a more straightforward, yet notably less accurate method. Initially, capture an image of a star and ascertain its position. Subsequently, endure for as long as feasible, 1 year, 5 years, 10. The greater the duration, the more advantageous it is. Subsequently, reassess the star's position and observe for any displacement about other stars or galaxies. Although it may appear straightforward, it is challenging and less precise than radial velocity measurements due to the difficulties in detecting minuscule movements across the sky. Space-based astrometry has superior accuracy. Hipparcos, an exceptionally successful satellite, has lately supplied astronomers with comprehensive astrometric data on stars up to the 12th magnitude, nearly 250 times dimmer than the weakest star perceivable by the human eye. The findings validate the non-existence of dark matter within the Milky Way's disk. Astronomers anticipate the forthcoming astrometric space mission, the European satellite Gaia, set for launch in 2011, which will deliver astrometric data for approximately 1 billion stars down to the 20th magnitude. If you can obtain a star's radial velocity and its transverse or proper motion, you may determine its true three-dimensional motion across space, referred to as its space motion. Despite advancements in methodology over the past century, quantifying the spatial motion of stars continues to pose significant challenges for astronomers. The mechanisms by which galaxies maintain their inflation. The analysis of stellar motions has been crucial in elucidating the shape and ascertaining the mass of the Milky Way galaxy. Upon observing a star system, one may inquire, what prevents this structure from collapsing inward upon itself? Only the movements of the stars inside a system such as the Milky Way sustain its expansion. This motion manifests in two forms, average and random. All stars traversing a vicinity around the Sun exhibit an average spatial motion, predominantly characterized by rotation, as the Sun and other stars revolve around the Milky Way. However, it is not a completely seamless motion. The stars move in distorted circular paths, resembling a poorly warped bicycle wheel, rather than in perfect circles. A typical star orbiting the Milky Way at approximately 8 kiloparsecs from the galactic center exhibits a nearly circular trajectory. 1 kiloparsec is approximately 3,262 light-years. As the star orbits the Milky Way, it exhibits a wobble around its circular path, occasionally approaching the galactic center and moving farther away, within an amplitude of 0.5 to 1 kiloparsec. These oscillations are markedly erratic. When positioned near the Sun and observing the transiting stars, one might discern that some oscillate inward, others outward, while some are at a pivotal juncture. The Milky Way exhibits an average round motion, resulting in its circular appearance and some random motion. Let us examine these two categories of motion, circular and random, in further detail. In pure rotation, all things rotate in a circular path. This necessitates an inside acceleration, an inward gravitational force, calculated as the square of the velocity divided by the radius. The internal gravitational attraction is contingent upon the location within the galaxy. If each particle in a galaxy orbits at the precise velocity corresponding to its radius, ensuring that the gravitational field supplies adequate acceleration for circular motion, the system achieves perfect circular motion. In such a system, random movements are non-existent. The contrasting extreme is a wholly stochastic system devoid of average rotation, wherein all stars converge toward the galactic center and subsequently disperse in arbitrary directions. This system would comprise stars of varying energy, located at different distances from the galaxy's core, with the entire structure sustained solely by the random motions of stars, which function similarly to the pressure in a gas. A galaxy of this nature would resemble a congregation of moths encircling a street lamp. In a genuine galaxy, it is, of course, a combination of both elements. Spiral galaxies, such as the Milky Way, predominantly exhibit rotation with minimal random motion, whereas elliptical galaxies display more random motion and diminished rotation. At every location within each galaxy, three factors must achieve equilibrium: the inward gravitational force and the outward pressure resulting from the random motions of stars must collectively furnish the acceleration required for average circular motion. Each of these three elements varies with location in the Milky Way. In 1919, the British scientist Sir James Jeans developed a series of equations linking these three variables. In the subsequent chapter, we shall explore Jeans' equations, a purely qualitative explanation. However, it is crucial to note that these equations connect mass and motion across diverse scales, ranging from interstellar molecular clouds, where stars originate, to the galaxies themselves. Jeans' equations, on a cosmic scale, connect the density of stars at a specific location in the Milky Way, the quantity of matter inside a defined volume, to the average and random motions of stars and the gravitational force present at that location. Astronomers have utilized Jeans' equations to ascertain the mass of the Milky Way, as inferred from the measured movements of the stars. The mass is indicated by the quantity of gravity required to equilibrate the movements of the stars, referred to as gravitational mass. The quantity of gravitational mass is adequate until juxtaposed with the mass indicated by the bright matter present in the Milky Way, the so-called luminous mass. In the early decades of the 20th century, quantifying visible stuff was quite an indirect process. Astronomers possessed a nebulous understanding of the types of stars present in the Milky Way. In 1924, British astronomer Arthur Stanley Eddington postulated a rough correlation between a star's mass and its absolute brightness, the brightness a star would exhibit at a standard distance of 10 parsecs. Ultimately, empirical studies of binary stars elucidated this link. The mass of a star is typically expressed by the Sun's mass, termed solar masses, with the Sun's mass designated as 1. Nonetheless, one should not presume that the correlation between absolute brightness and mass is uniform across all stars. A big star typically exhibits high brightness, resulting in a low mass luminosity ratio. In other words, a significant amount of brightness is relative to a specific mass. Conversely, diminutive stars, significantly smaller than the Sun, exhibit a lack of luminosity relative to their mass. The mass-luminosity ratio is exceedingly high here. The mass-luminosity correlation for stars of varying brightness has been extensively examined over the years and is now comprehensively understood for most stars in the Milky Way. Consequently, by aggregating the masses of stars with varying luminosities in the proportions observed in the Milky Way, one can derive an informed estimate of the galaxy's luminous mass. This methodology was first employed in the 1920s, and while contemporary estimates are often generated through theoretical approaches, such as simulating populations of virtual stars via computer, the results remain largely consistent. The dilemma confronting astronomers investigating the dark matter issue has now arisen. Were only stars and gas present, the gravitational and luminous mass of the Milky Way would be identical. However, as you may have surmised, they are markedly dissimilar. Who is the discoverer, and who will be the focus of the subsequent chapter in our narrative? We must revisit the past to elucidate how observing star movements culminated in identifying dark matter. Nevertheless, we must revert to the 1920s, an era when our comprehension of the magnitude, characteristics, and genesis of the universe was swiftly evolving. This historical period parallels the initial era of the telescope, during which the universe transitioned from a localized, geocentric model to a framework in which Earth is only another planet orbiting an average star. By the 1920s, numerous astronomers embraced the galactic model posited by Jacobus Cornelius Kapteyn. In 1901, a vast elliptical assembly of stars, with our solar system positioned toward the center. Despite not publishing his theory for almost 2 decades, Kapteyn's model was widely recognized among his peers, including the youthful Hendrik Oort, whom we shall encounter shortly. Despite the popularity of Kapteyn's model, the research conducted by other astronomers, including Americans Harlow Shapley and Heber D. Curtis, demonstrated that the Milky Way was significantly larger than Kapteyn had proposed. Researchers discovered that the peculiar spiral-shaped nebulae, formerly believed to be components of the Milky Way, are, in fact, vast galaxies, located at significant distances from our galaxy. Astronomers, including Vesto Melvin Slipher and subsequently Edwin Hubble, conducted additional observations employing procedures akin to those used in the spectral line observations detailed in the previous chapter. Most of the galaxies exhibited a redshift, signifying their recession from the Milky Way. This discovery indicates that the universe is expanding, with each galaxy moving away from all other galaxies, rather than suggesting that the Milky Way occupies a central position in the universe. The reciprocal recession of galaxies is frequently shown by envisioning sultanas within a fruitcake, baking in an oven. As the cake ascends, each sultana separates from the others, propelled by the growing cake. While Hubble recognized the phenomenon of universal expansion, it is important to acknowledge that his observations of retreating galaxies were predated by Slipher, the foremost expert on galactic velocities during that period. Hubble discovered a fundamental law that correlates distance with recession velocity. A significant implication of the reciprocal recession of galaxies is that the greater the velocity at which a galaxy recedes from an observer, the more distant it is. Consider 3 galaxies uniformly spaced along a linear trajectory, all receding from one another at an identical velocity. Envision our existence in a galaxy situated at one extremity of the continuum. From our viewpoint, the intermediate galaxy will be receding from us, just as we will be distancing ourselves from the residents of that galaxy. Nonetheless, the recession of the more distant galaxy, which is twice as far away, would occur at double the velocity of the nearer galaxy. This occurs because it is moving away from the closer galaxy, which is also moving away from us. The higher the recession velocity of a galaxy, the greater its distance. The recession velocity is proportional to distance, resulting in a nearly constant velocity-to-distance ratio throughout different galaxies. Establishing the Hubble constant has become a significant challenge. A primary reason is the considerable difficulty in accurately determining distances to galaxies. Hubble gave minimal consideration to the theoretical underpinnings of the universe's potential expansion. While Hubble and Slipher examined the retreating galaxies, various theorists, including Albert Einstein, formulated a theoretical framework for an expanding universe. A significant consequence of an expanding cosmos is that all existence commenced at a specific point in the past. This occurrence is referred to as the Big Bang, and, is essential to our narrative of dark matter. We will examine its complexities in greater detail subsequently. One of the titans of 20th century astronomy, Hendrik Oort, emerged during this era of discovery. Despite the current belief that his conclusions regarding dark matter are erroneous, Oort, more than any other individual, motivated astronomers to contemplate dark matter on a galactic scale earnestly. Despite his little stature, Oort was a formidable individual with a commanding presence. During World War II, he declined to collaborate with the German authorities and vacated his position at Leiden University to pursue his studies from a cottage in the Dutch countryside. Oort acquired international esteem and exerted considerable political influence in the Netherlands from a young age. Following his retirement, he continued his studies nearly until his demise at 92 and remained proficient in ice skating well into his 90s. The Netherlands possesses a rich and enduring legacy in astronomy, which Oort perpetuated and directed. In 1935, he assumed the role of Professor of Astronomy at Leiden Observatory during the nascent phase of radio astronomy in Australia and the United States. He developed a growing fascination with radio astronomy, recognizing that radio waves could traverse the obstructive gas and dust clouds of the galaxy, as well as the atmospheric clouds prevalent in Dutch skies throughout most evenings. Consequently, it is unsurprising that after the Second World War, he and his associates acquired a German 7.5-meter radar dish, transformed it into a radio telescope, and employed it for pioneering research. Henk van der Hulst, a student of Oort, forecasted the emission of the renowned 21 centimeter spectral line of neutral hydrogen. Astronomers in Leiden first detected the hydrogen gas within the Milky Way's interstellar medium, facilitating the examination of its rotation. These investigations, conducted by astronomers in the United States and Australia, validate the long-held hypothesis on the spiral structure of the Milky Way. These insights were historically significant. Oort recognized that the Netherlands required a contemporary radio telescope significantly larger than the 7.5-meter German antenna previously employed. In 1956, he played a pivotal role in establishing a 25-meter antenna at Dwingeloo in the northern Netherlands. And in 1970, he contributed to the development of the Westerbork radio synthesis telescope. The Westerbork instrument is a huge interferometer of 14 25-meter dishes arranged along a 2.8-kilometer east-west track, resembling the Australia Telescope Compact Array, ATCA, but larger and more potent. Chapter 4 will demonstrate that the Westerbork telescope was essential in leading astronomers to understand that spiral galaxies are predominantly composed of dark matter rather than stars. In summary, Oort's impact in this domain was substantial. However, we should revert to the narrative of his prior studies. A significant early discovery from the examination of stellar motions was the rotation of the Milky Way. Three prominent individuals contributed to discovering the galaxy's rotation between 1925 and 1930. Gustav Stromberg, Bertil Lindblad, and Jan Oort. Stromberg's contribution was identifying a correlation between the average motion of Milky Way stars and their random motions. The greater the random motion of a specific class of star, the larger their average velocity about the Sun. The erratic movements of the stars function similarly to gas pressure, and in conjunction with rotation, they assist in sustaining the galaxy against its inherent gravitational pull. Stromberg's discovery provided significant evidence that we inhabit a revolving galaxy. Lindblad was the first to demonstrate that the Milky Way is rotating, with stars following nested orbits around the galaxy's center, analogous to the planets orbiting the Sun, albeit more complex. Lindblad's mathematical publications motivated several astronomers, including Oort, to investigate the migration of stars within the galaxy. Oort's contribution was his discovery, 1927, of the galaxy's asymmetrical rotation. He recognized that the disk-shaped galaxy did not rotate uniformly like a car's wheel, where all components revolve for the same duration. Instead, the inner sections of the galaxy rotated more rapidly than the outside regions. Each point in the galaxy exhibits a distinct angular velocity, rendering the motion of stars and gas in the Milky Way analogous to the vortex formed as bath water drains into a plug hole. Despite its simplicity, this represented a significant accomplishment when the galaxy's structure, namely its spiral configuration, had not yet been validated. Oort's fascination with galactic dynamics culminated 1932 in a comprehensive analysis of the stuff contained within the galaxy's disk. Kapteyn and Jahns had previously indicated skepticism over the existence of unseen stuff in the Milky Way. Nonetheless, Oort conducted the inaugural comprehensive investigation of the issue. Oort analyzed the average, random, and perpendicular movements of stars inside the Milky Way to assess the matter concentration of its disk. Stars orbit the galactic disk, while simultaneously oscillating vertically through the plane of the galaxy, akin to toy horses on a merry-go-round. Stars' average, rotational, and random motions inhibit their collapse toward the galaxy's center, while their vertical motion prevents the galaxy from forming a shape akin to a totally flat disk. One of Jean's equations correlates the average, rotational motion, random motion, and gravitational force inside the plane of the galaxy. Another Jean's equation correlates stars' vertical motion with the disk's gravitational field. The gravitational attraction that attracts all stars toward the galactic plane is counterbalanced by the random vertical motions of the stars, which function similarly to pressure in a gas. Upon believing he had identified dark matter within the disk, Oort was examining vertical star motions. Nevertheless, this endeavor is fraught with complications. In Oort's situation, an error occurred. Observe the star's erratic vertical movements and their orientation perpendicular to the disk to ascertain the matter density of the disk. Nevertheless, the Jean's equations are rather particular regarding the stars in the analysis. To obtain accurate density and velocity data, it is imperative to utilize identical stars. Otherwise, the results will be flawed. This is where Oort erred. Astronomers measured the vertical distribution of stars perpendicular to the galactic disk by counting all visible stars within a specified sky area that constituted a vertical column to the disk. They analyzed the stars' spatial arrangement within the column by analyzing their luminosity distribution. Observing a greater number of bright stars than faint stars suggests that a higher concentration of stars is situated in proximity rather than at a distance. Conversely, a scarcity of bright and faint stars, coupled with an abundance of stars of intermediate brightness, indicates the presence of a layer of stars at a certain intermediate distance, and so forth. This overlooks significant factors, particularly that not all stars possess the same intrinsic luminosity. It also neglects to account for the interstellar darkening caused by dust along the line of sight.
The issue with K-stars.
We assessed the vertical movements of the stars utilizing the Doppler effect. During the 1920s and 1930s, astronomers lacked the advanced detectors, spectrographs, and large telescopes available today, prompting them to select the most accessible stars for measurement. K-giants are particularly appealing to astronomers for velocity measurements. The letter K originates from the renowned Hertzsprung-Russell diagram, juxtaposing a star's luminosity and spectral temperature. These older stars have depleted most of their hydrogen reserves and expanded to vast sizes, generally 30 times the Sun's diameter, making them approximately 100 times more luminous and thus more visible. Equally significant, They are cold stars with numerous readily discernible spectral lines for measurement. Hot stars typically exhibit fewer spectral lines for reasons not pertinent to this discussion. Oort presumed, as did all astronomers until the 1980s, that these K-giants were representative members of the galactic disk. However, they are not. The disk of the galaxy is highly intricate, and in addition to the thin disk depicted in edge-on spiral galaxy photographs, a rather diffuse structure, known as the thick disk, was identified in 1983. The thick disk is roughly 4 to 5 times thicker than the thin disk, which is well known, and populated with ancient stars, including the readily identifiable K-giants. The stars in the thick disk likely formed during the primordial stages of the galaxy. One issue that confounded Oort's estimates was that the stars in the thick disk generally possess double the random velocity of those in the thin disk, accounting for the thick disk's greater thickness. These vigorous thick disk stars disguised themselves as thin disk stars and infiltrated Oort's computations. Their increased vertical movements likely influenced his assertion that the star's average vertical motion inside the galaxy's disk was significantly higher than it actually is. Oort deduced that the significant average vertical motion indicated the presence of substantially more matter, potentially double that represented by the stars of the Milky Way, to maintain the integrity of the disk. If such substance existed, it was entirely dark. Oort persisted in his investigations of disk dark matter during the 1940s and 1950s. The topic remained mostly inactive until the 1970s, when American astronomer John Barkall, head of the astrophysics group at the Institute for Advanced Study in Princeton, conducted a comparable analysis to Oort's using more contemporary data. Barkall's findings were largely consistent with Oort's, yet they catalyzed numerous other inquiries into the concept of disk dark matter. At this point, the concept of dark matter in the outer regions of galaxies had gained widespread acceptance, leading to significant interest in determining whether dark matter was also genuinely present in the disks of galaxies. This marked the onset of the conclusion for disk dark matter. The subsequent independent studies consistently yielded disk dark matter values lower than those of Oort or Barkall. In 1988, a significant setback for disk dark matter occurred when Konrad Kuijken, a Belgian student collaborating with Jerry Gilmore at Cambridge, published a pivotal series of papers in the monthly notices of the Royal Astronomical Society, proposing that there was minimal, if any, dark matter in the Milky Way's disk. The divergent conclusion about the disk dark matter is partially attributable to an enhanced mathematical technique for quantifying the gravitational mass within the galaxy's disk. The Jeans equations, employed by previous researchers, originate from the more fundamental Boltzman equation, which pertains to phenomena in both spatial and velocity domains. Rather than stating that a specific region in space contains a certain number of solar masses per cubic parsec in 3-dimensional space, the Boltzmann equation employs a density d defined in 6-dimensional space. This signifies the following. We occupy a location within the galaxy and inquire, what is the density of solar masses per cubic parsec? We inquire about the density in velocity space. What is the quantity of solar masses per cubic parsec or per cubic kilometer per second in this context? The phase space density, typically represented as F, quantifies the number of stars with a specific velocity inside a defined volume of space. The Boltzmann equation delineates the density variation as a function of velocity and position, hence contingent upon the gravitational force. The phase space density comprehensively characterizes the star system, rendering it a more fundamental equation. Notwithstanding its limitations, this technique circumvents certain variables of the Jeans equations that are challenging to quantify. Currently, most astronomers contend that the Milky Way's disk contrary to Oort's assertion, is largely devoid of dark matter. A 1998 study by Olivier Bienheim and associates in France significantly reinforced this conclusion. Utilizing densities and motions of stars observed by Hipparcos, they demonstrated that the gravitational density of the disk approximates that of observable objects. It is important to emphasize that this does not inherently signify the conclusion of disk dark matter. Rather, the prevailing perspective is that there is minimal, if any, dark matter in the disk. Indeed, the presence of dark matter in the disk would significantly simplify astronomical life, as it would elucidate various known phenomena. The absence of disk dark matter currently results in the Milky Way's disk being less massive than that of most comparable galaxies. This is a persistent concern. Is our galaxy peculiar, or are some methodologies employed for measuring other galaxies flawed? Numerous astronomers regard the lack of dark matter in the disk as unsettling and would favor its presence at approximately double the current amount. Although seemingly erroneous, Oort's finding of disk dark matter would yield a significantly more palatable outcome. Astronomers remain uncertain about the validity of the prevailing conclusion, that the disk contains no dark matter, despite widespread belief to the contrary. Additional, minor, perplexing aspects emerge. However, for two reasons. Oort's mistaken belief in disk dark matter was not merely a misleading hypothesis. Initially, it contributed to the enhancement of the current galaxy model. In 1922, Oort examined the motion of enormous spherical aggregations of stars, known as globular clusters within the galaxy. Most galaxies, including the Milky Way, include compact assemblages of approximately 1 million stars, referred to as globular clusters. Oort determined that the gravitational force of luminous matter alone cannot retain globular clusters inside the galaxy because of their fast motion. A basic star chart indicates that globular clusters congregate at the center of the galaxy, oriented towards the constellation Sagittarius. This asymmetrical distribution in the sky strongly indicated to Oort that the globular clusters are integral to the galactic system, rather than merely traversing it. According to Kapteyn's concept, the galaxy must possess a mass 200 times greater than that of its stars to maintain their known velocities. This ignited interest in the concept of unseen, dark matter, and prompted a re-evaluation of the size and structure of the Milky Way. Secondly, the episode imparts a significant lesson regarding the essence and methodology of science. Several decades after Oort's statement, dark matter constituted half of the galaxy's disk before astronomers conducted more investigations into the issue. One might assume that a significant finding by a prominent astronomer would have garnered major attention from the scientific community and prompted further investigation. The reasons for the lack of follow-up remain speculative. At that time, the concept of dark matter was not integrated into conventional astronomical discourse. Nevertheless, astronomers regarded Oort's finding as excessively serious. His dominance was so pronounced that astronomers believed they could not surpass his published findings. Bahcall's re-examination of the issue resulted in Oort's mistake being identified. The takeaway is to avoid placing excessive trust in any outcome, regardless of the stature of the scientist who produces it. Science flourishes and develops through doubt and skepticism. In their absence, it becomes stagnant. Oort's research and esteemed status as a prominent scientist catalyzed the notion of dark matter on a galactic scale, notwithstanding its initial shortcomings. Shortly after he proclaimed the presence of dark matter within the galactic disk, one of his peers revealed its existence on a broader scale and substantially greater amounts. Only the disparity between the two guys aligns with Oort's findings. Shortly after Oort proclaimed the presence of dark matter within the Milky Way's disk, astronomer Fritz Zwicky declared its existence in individual galaxies and galaxy clusters. During an era when most astronomers failed to recognize that our galaxy was a relatively typical assembly of stars akin to other galaxies in the universe, Zwicky was already acknowledging a universe replete with thousands of galaxies, characterized by large-scale structures and populated with extraordinary phenomena, such as neutron stars and dark matter. Zwicky was an exceptional scientist who significantly contributed to astronomy and other fields. He was born in Bulgaria to Swiss parents and spent most of his professional life in America. Upon obtaining a PhD in physics from the Swiss Federal Institute of Technology, Zurich, in 1922, he relocated to the United States, where he was a faculty member at the California Institute of Technology, Pasadena, from 1925 until 1972. Notwithstanding his residency, he encountered a rejection of American citizenship in 1949. Zwicky's astronomical achievements go beyond the mere finding of large-scale dark matter. In 1934, he elucidated the distinction between novae and supernovae in conjunction with Walter Baade. They demonstrated that supernovae transpire significantly less often than novae, and accurately proposed that supernovae are the consequence of the demise of big stars. They suggested that the aftermath of a supernova explosion would comprise a neutron star alone. Appendix 1 comprehensively describes the neutron, a small neutral particle found in the nucleus of most elements. Discovered in 1932 by James Chadwick, it is reported that within hours of learning about the discovery, the substantial Russian physicist Lev Landau envisioned an extraordinarily compact and dense star, primarily composed of neutrons. However, it was Baade and Zwicky who 2 years later elucidated the process by which an ordinary star may transform into a neutron star. With certain modifications, the narrative they recounted persists fundamentally unchanged today. All stars are spherical bodies composed of heated gas. The continuous energy emission from the star's core preserves its spherical shape against gravitational forces, notwithstanding its colossal dimensions. This energy originates from the fusion of lighter elements with heavier counterparts. As long as the star is provided with nuclear fuel, such as hydrogen in the Sun's case, it can sustain its resistance to the inward force of gravity. Nevertheless, all stars ultimately deplete their nuclear fuel, resulting in the cessation of energy emissions. A tiny star of solar mass undergoes a comparatively tranquil extinction. Devoid of external support, its core implodes into a white dwarf approximately the size of Earth, while the outer layers are expelled into space, creating a stunning planetary nebula. Conversely, a more massive star concludes its existence somewhat more dramatically. Depleting its nuclear fuel source, it implodes dramatically. The significant implosion leads to a core bounce, causing most of the star's outer layers to detonate with the luminosity of 1 billion stars. Simultaneously, the star core persists in its fall. The core, possessing a mass comparable to the Sun, would contract to a diameter of approximately 20 kilometers. At this density, electrons and protons would amalgamate to create neutrons, resulting in a thimble-sized quantity of the substance weighing 100 million tons. Validation of Zwicky and Baade's hypothesis would require an additional 35 years. Zwicky also anticipated that dark matter in the universe may be delineated by gravitational lensing, which will be discussed in depth later in this book. The fundamental concept is that the gravitational fields of big entities can alter the trajectory of starlight. The concept is predicated on Einstein's general relativity prediction. Light adheres to the local curvature of space-time around a massive object. The respected British astronomer Arthur S. Eddington validated Einstein's prediction during a notable voyage to observe the deflection of starlight during the complete solar eclipse of 1919. Despite the expedition's success, and the validation of Einstein's prediction, which catapulted him to unforeseen prominence. Both Einstein and Eddington harbored reservations regarding the phenomenon's practical utility in scientific inquiry. One possibility was the concept of gravitational lensing, in which the gravitational field of a galaxy bends and magnifies the light from more distant galaxies, similar to how a magnifying lens focuses sunlight, a phenomenon familiar to children, often at the expense of unsuspecting insects. Notwithstanding Einstein and Eddington's skepticism, who deemed the probability of alignment negligible, Zwicky anticipated that gravitational lensing might prove beneficial for investigating objects at the extreme boundaries of the universe. His prognosis was exceedingly profound. We will demonstrate that gravitational lensing is now widely employed in the pursuit of dark matter within the galaxy and in galaxy clusters, yielding remarkable success. In addition to these contributions, Zwicky also engaged in research encompassing cosmic rays and the development of early jet engines. Few scientists possess intellects decades ahead of their contemporaries, although Fritz Zwicky undoubtedly exemplified this exceptional quality. On a personal level, he was an outspoken individual with a pronounced accent, despite being in the United States for nearly 5 decades. He was ostentatious, egotistical, and had a disparaging view of numerous co-workers. One of his preferred insults was to label disapproved individuals as spherical bastards. As he elucidated, they were bastards, regardless of the perspective from which they were viewed. Zwicky was primarily an observational astronomer and conducted significant theoretical research. He was among the initial individuals to demonstrate that the perceived concentrations of galaxies, originally noted by Herschel, were, in reality, genuine clusters. He identified several galaxy clusters utilizing the 48-inch Schmidt telescope at Mount Palomar Observatory. For instance, when the cumulative count of supernova discoveries reached 12 between 1937 and 1941, Zwicky identified an additional 18 in different galaxies. In his later years, he compiled extensive lists of galaxies, yet his bitterness persisted. As he grew increasingly resentful of the external world's treatment of him, he composed a scathing foreword to his 1971 catalogue of selected compact galaxies and post-eruptive galaxies, portions of which provide an engaging reading. Below are a few examples. The naivety of certain theoreticians is consistently astonishing. We need only reference the eminent figure in American astronomy, Henry Norris Russell, who in 1927 asserted, "The attributes of the stars are contingent upon the most elementary and fundamental laws of nature, and even with our current understanding, could have been anticipated from general principles had we never observed a star." Henry Norris? Russell was a prominent astronomer who significantly advanced star astronomy, and most contemporary astronomers would likely not contest his declaration. Zwicky was evidently frustrated by his inability to utilize the Mount Palomar 200-inch telescope until the latter part of his career. He composed, "During the 1930s, the most distinguished observational astronomers made assertions that have since been demonstrated to be entirely incorrect. Consequently, E.P. Hubble, W. Baade, and their youthful acolytes, who sought to ingratiate themselves, manipulated their observational data, concealed their shortcomings, and persuaded the majority of astronomers to accept and endorse their biased and erroneous presentations and interpretations of facts." Like several other human endeavors, astronomy has consistently encountered disruption from powerful individuals inside its hierarchical structures. The superfluous content in the overflowing astronomical journals provides compelling evidence. Zwicky consistently selected notable subjects for his criticism. Hubble and Baade were pivotal astronomers of their era, and their discoveries regarding the universe's expansion and the types of stars within galaxies are undeniably significant. in stark contrast to their uncritical acceptance of various childish fantasies and appropriated ideas, the editors of the Astrophysical Journal demonstrated an astonishing lack of tolerance and sound judgment. By rejecting my initial comprehensive and observationally substantiated article on compact galaxies. This coincided with the discovery of quasars, extremely luminous and remote entities. Zwicky's colleagues occasionally mirrored his disdain. He authored a book titled Morphological Astronomy, which elucidated morphological arguments for using patterns to ascertain the essence of entities. The book extensively exposes various perspectives he has formulated over the years. Nonetheless, it encompasses several insights that retain their relevance in contemporary times. It encompasses early instances of composite imaging, wherein a negative print of a galaxy in one wavelength band, e.g., yellow light, is superimposed on a positive print in another wavelength, e.g., blue, to illustrate the distribution of various types of stars within the galaxy. Nonetheless, the majority of individuals overlooked this book. It is said that his book was categorized in the fiction department at an observatory library, frequented by Zwicky, except during his visits, when it was repositioned under Z in the science section. Zwicky was unafraid to confront significant astronomy inquiries and was keen on ascertaining the mass of both extragalactic nebulae, galaxies, and galaxy clusters. Circa 1933, he disseminated his initial publications on these topics in German. In 1937, he authored a comprehensive paper for the Astrophysical Journal, delineating the foundational concepts of mass measurement that would be explored in the subsequent 60 years, including the virial theorem, a technique for determining the mass of a galaxy or galaxy cluster, which will be described shortly. He elucidated the methodology employed to identify dark matter within galaxy clusters. Just as we may infer the mass of a galaxy from its gas and stars, we can deduce the mass of a galaxy cluster from their movements. Zwicky's research on galaxy clusters introduced a novel method for quantifying mass in the universe. Galactic clusters. A substantial sample is essential for examining the behavior of galaxies in groups, and some galaxy clusters are well suited for this objective. The history of galaxy clusters begins with William Herschel, who, in the 1780s, observed that galaxies, referred to as nebulae at the time, were not randomly scattered in the sky, but seemed to cluster in groups. Herschel observed a particular assembly inside the constellation Virgo. In 1933, Harlow Shapley released a compilation of 25 galaxy clusters. He asserted that the groups were not mere coincidences, but rather the outcome of an evolutionary process. His research on Cepheid variable stars within globular clusters contributed to elucidating the true size of the Milky Way. Until the 1950s, the majority of astronomers regarded galaxies as solitary entities, with only a limited number exhibiting any genuine physical association with others. However, evidence indicating that galaxies were sociable began to accumulate. In 1958, George Abel released a catalogue of 2,712 galaxy clusters, and then, from 1960 to 1968, Zwicky and colleagues published catalogues of 9,134 galaxy clusters. These significant works were produced by analyzing the photographic plates captured with the 48-inch Schmidt at Palomar, assembled into the National Geographic Society Palomar Observatory Sky Survey, POSS. The significant disparity in the galaxy count is attributable to the differing methodologies employed by the two astronomers in their classification of clusters. Abel focused exclusively on the most densely populated clusters, whereas Zwicky included all aggregates, regardless of their sparsity. Since then, more advanced observational techniques and statistical methodologies have demonstrated that most galaxies are part of groupings and clusters, with only a few existing in isolation inside the universe. Galaxies exhibit a variety of forms and dimensions. We inhabit a flattened disk characterized by an interior spiral configuration. Spiral galaxies are typically abundant in gas, dust, and stars, existing in two varieties: classic spirals that resemble cream swirling on the surface of newly mixed coffee, and barred spirals with central bars from which the spiral arms emanate. Conversely, elliptical galaxies exhibit no internal structure, possess negligible gas or dust, and resemble flattened spheres. Finally, the gas-rich galaxies, termed irregular because of their indistinct morphology, are present. The Small Magellanic Cloud exemplifies this category. In 1925, Hubble proposed a system to correlate the classifications of galaxies. Despite ongoing ambiguity over the origins of many galaxy types, current observations of increasingly distant galaxies, those that lived nearer to the universe's inception, reinforce the connection between morphology and galactic evolution. Although individual galaxies can be categorized by their morphology, galaxy clusters exhibit identifiable traits. Abel and Zwicky were the pioneers in classifying sorts of clusters. Abel categorized them as regular or irregular, whereas Zwicky classified them as compact, medium, or open. Neither classification system considered the types of galaxies inside clusters, based exclusively on the spatial arrangement of the constituent galaxies. William W. Morgan was the first to investigate the characteristics of the individual clusters. He meticulously examined several adjacent galaxy clusters, concentrating on the more luminous members, within 2 magnitudes of the brightest member. He identified 2 categories, one characterized by a dispersion of primarily spiral galaxies, with only the most luminous being elliptical, or S0, flattened like spirals but with minimal gas, and another that is denser, where all the most luminous members are elliptical or S0 galaxies, accompanied by a limited number of fainter spirals. Similar to individual galaxies, these attributes indicated a correlation between a cluster's form and surroundings. Galaxy clusters are currently categorized as either regular or irregular. Regular clusters are approximately spherical collections of galaxies, predominantly composed of elliptical or S0 galaxies. They are affluent and concentrated, potentially containing 5 to 10% of the galaxies in the universe. Irregular clusters lack a recognizable shape and may encompass any galaxy. These clusters are dense and resemble aggregations of smaller clusters, containing between 10 and 1,000 galaxies, while smaller clusters, approximately 3 million light-years in diameter, are more prevalent. Numerous clusters of galaxies have been identified, and their examination has yielded valuable insights for astronomers in areas such as galaxy formation and evolution, high-energy astrophysics, large-scale structure, and cosmology. The cluster utilized by Zwicky for his research on dark matter is catalogued as 1656, in Abel's catalogue, and is located approximately 90 megaparsecs distant in the northern constellation of Coma Berenices. Commonly called the Coma cluster, this extensive cluster, one of the most affluent identified, was initially documented by Max Wolf, utilizing the Bruce telescope at Heidelberg, Germany, in 1901. The roughly spherical structure is partitioned into 2 components, each approximately equal in size and centered around a galaxy associated with a radio source. The Coma cluster serves as an exemplary subject for observation. It is located in an area of the sky distant from the plane of the Milky Way, therefore remaining unobscured by stars, gas, or dust. In 1957, Zwicky identified 804 galaxies, exceeding magnitude 16.5 within around 2.5 degrees from the cluster's nucleus, and 29,951 galaxies, surpassing magnitude 19 within 6 degrees. These galaxies are not associated with the Coma cluster. Yet the system is expected to include over 1,000 galaxies, categorizing it among fewer than 5% of Abel's clusters with such a quantity. The Coma cluster's predominantly elliptical and S0 galaxies are thought to be among the first to have formed in cosmic history. Two massive elliptical galaxies, NGC 4889 and NGC 4874, dominate the cluster, perhaps attaining their substantial size by absorbing or cannibalizing smaller galaxies throughout their extensive lifespans. The previous film illustrated how Oort and others quantified the mass of the Milky Way by analyzing the velocity of its constituent stars. Notwithstanding the substantial disparity in size and mass, the mass of a galaxy cluster is assessed comparably. A significant distinction is that in a galaxy cluster, the predominant motion is not rotation, but rather the random motion of all the galaxies. Fortunately, numerous solutions exist to address these motions. A cluster functions similarly to the gas pressure within an inflated balloon. The balloon remains inflated due to the equilibrium between the random motion and pressure of the air molecules within and the tension of the rubber outside. Likewise, an elliptical galaxy or a galaxy cluster is sustained by the pressure generated by the movements of its components, stars within a galaxy or galaxies within a cluster, that counteract the inward force of gravity. The pressure can be quantified by assessing the velocity of galaxies within a cluster, which allows for the determination of the requisite gravitational field and corresponding mass necessary to confine the galaxies. The work becomes difficult due to the necessity of making specific assumptions regarding the extent of random motion. For example, we would obtain a singular mass number if each galaxy traversed radially in and out of the cluster's center. However, that would constitute an atypical scenario, as most galaxies do not traverse a radial orbit directly past the cluster's core. Some traverse circular paths, while others follow radial orbits. Nonetheless, the majority navigate the cluster through various combinations of these extremes. Consequently, we presume that the configurations of orbits fluctuate randomly. Another factor to consider is that systems such as gas clouds or galaxy clusters represent a balance between gravity and pressure, and between gravity and the pressure gradient, specifically, the variation of pressure with distance from the system's center. No pressure differentials are present if the pressure is uniform throughout the system. A pressure force exerts an outward push when the pressure in the center exceeds that in the peripheral areas. An exemplary case is a solitary star, wherein the pressure at the core significantly exceeds that of the outer layers. The gas's pressure gradient exerts an outward force on the star's mass, attempting to induce expansion, while gravity counteracts this effect. Moreover, the arrangement of all system components, be it gas molecules or galaxies inside a cluster, is crucial while assessing a pressure gradient. Despite the ambiguous definition of galaxy clusters, one may analytically establish an average radius for a cluster, enabling the calculation of the pressure gradient within the cluster. Zwicky analyzed the movements of over 600 constituent galaxies to ascertain the random motions inside the Coma cluster. Due to their vast distance, detecting any movements of the galaxies in the cluster along our line of sight is unfeasible, as the perspective at such distances is severe. By analyzing the Doppler shift of the spectral lines from several galaxies, he determined their velocities relative to the average motion of the entire cluster. This task is arduous and was challenging at the time. The Coma cluster is receding from us at an average rate of 7,000 km/s. This is merely an average velocity comparable to a swarm of bees departing from our position at a defined pace. Certain bees will move away more rapidly than others at any moment, according to their activity within the swarm. The movements of galaxies inside the Coma cluster indicate that some are receding from us at higher velocities than others, despite the entire cluster's overall recession. If a galaxy in the Coma cluster is receding from us at 5,000 km/s, it indicates it is approaching us relative to the cluster at 2,000 km/s. Similarly, if a galaxy is observed receding from us at 9,000 km/sec, it departs from the cluster's center at a 2,000 km/sec velocity. Neither of these galaxies, however, will extricate themselves from the cluster, any more than the stars spotted by Oort will extricate themselves from the Milky Way. The cluster's gravitational field is sufficiently robust to capture possible escapees. Over time, the cluster's gravitational field is sufficient to alter the galaxy's orbits and pull them back toward the core. The crucial aspect is that an increased disparity in velocities, which signifies the total kinetic energy of the system, necessitates a bigger gravitational energy to maintain the galaxy's cohesion. As gravity necessitates the presence of matter, a direct comparison of kinetic and gravitational potential energy reveals the system's mass. As previously stated, despite the significant disparity in magnitude between a single galaxy and a cluster of galaxies, the correlation between kinetic and gravitational potential energy is a shared factor in investigating dark matter at both galactic and galaxy cluster levels. The computation is more complex for irregular systems, such as galaxy clusters, where movements are less distinct. Nevertheless, Zwicky determined the gravitational mass of the Coma cluster with a method referred to as the virial theorem, derived from the Jeans equations utilized by Oort. This illustrates the kinetic energy a system possesses due to the motion of its components, such as galaxies within a cluster, and the gravitational potential energy required to maintain its structural integrity. Zwicky computed the mass attributable to each galaxy, utilizing the gravitational mass of the Coma cluster. He may not have been entirely accurate, as scientists at that time were uncertain about the mass of an individual galaxy and its stars, a challenge that persists today. Nonetheless, Zwicky quantified the luminosity of each galaxy in his images and derived a relatively precise estimation of the cluster's overall brightness, akin to Oort and others who posited that the luminous mass of a galaxy could be determined by tallying the stars and applying the stellar mass-luminosity correlation. His presumption that the stellar composition of each galaxy was analogous continues to be employed by astronomers today. The procedure was quite complex. Assess the brightness, velocity, and position of individual galaxies inside a cluster, subsequently inferring the luminous mass of the cluster. Zwicky identified a difference between luminous and gravitational masses when conducting this analysis. Had the cluster included solely luminous matter, the velocity of the individual galaxies would have propelled them to the distant confines of the universe ages ago. This was evidently not the situation. Thus, some force exerted sufficient gravity to maintain the cohesion of the cluster. However, the quantity of stuff implicated was remarkable, so significant that it required decades for the astronomical community to completely acknowledge Zwicky's findings. While Oort astonished many by asserting that the galaxy harbored potentially double the visible matter in stars, Zwicky's findings uncovered a significantly greater disparity between luminous and gravitational mass. His estimates indicated that the Coma cluster possessed up to 50 times the luminous material in an undetected form. Dark matter permeated the Coma cluster. In 1933, Zwicky conducted this research, and 3 years later, Sinclair Smith performed a comparable experiment with the Virgo cluster at Mount Wilson Observatory. This cluster of galaxies is significantly closer and exhibits an uneven shape. The Virgo cluster, due to its immense mass and proximity, is attracting our small group of galaxies. The local group of galaxies comprises two prominent spiral galaxies, the Milky Way and the Andromeda galaxy, alongside numerous dwarf, elliptical, and irregular galaxies. Like innumerable other historical and prospective galaxies, our galaxy may ultimately yield to this Virgo-centric flow and integrate into it. The center part of the Virgo cluster is primarily characterized by a massive elliptical galaxy, whereas most of the cluster's observable mass consists of a hot gas ranging from 10 to 100 million degrees that pervades the cluster. Smith revealed the concealed enigma of the Virgo cluster. Upon conducting analogous calculations on the Virgo cluster, as Zwicky did on the Coma cluster, he deduced that it harbored an extraordinary 100 times more dark matter than luminous matter, likely between the galaxies. The virial theorem provided a compelling rationale for the existence of dark matter. Following Zwicky's research on the Coma cluster, scholars have employed the same methodology on numerous additional clusters, producing analogous outcomes. Astronomers were discovering that the universe was becoming increasingly obscure and enigmatic, rather than elucidating its nature. Astronomers employ arguments that are more advanced than Zwicky's original propositions. For the past 25 years, Oort's dark matter hypothesis has influenced most astronomers more significantly than Zwicky's, despite Zwicky's argument being far more severe. Certain individuals have conjectured that this resulted from the contrasting personalities of the two astronomers. The disparity between these two formidable individuals was strikingly pronounced. Oort was the foremost Dutch astronomer of his era, esteemed and venerated by his contemporaries in the field. Zwicky was an irascible individual who enjoyed disputing his fellow astronomers' firmly held scientific convictions, regardless of their nature. He was, succinctly, both invigorating and exasperating. However, an alternative argument is that Zwicky's findings, which necessitated up to 50 times more dark matter than luminous matter, challenged the comprehension of astronomers. Although all astronomers have been cognizant of Zwicky's findings for the past 50 years, they prefer disregarding them rather than embracing the necessary implications. By the conclusion of the 1930s, two prominent astronomical authorities asserted that a significant portion of the universe is composed of dark matter. However, dark matter remained inactive for 4 decades, as significant astronomical discoveries and concerns over illuminating matter gained prominence. This encompassed the development and competition between the steady state and Big Bang theories on the universe's origin, and the identification of pulsars, radio galaxies, and the most luminous entities in the universe, known as quasars. Quasars, the active nuclei of far galaxies, are among the oldest objects in the universe. They are exceedingly luminous, radiating more energy than 100 supergiant galaxies. Black holes and the cosmic microwave background radiation, the remnant of the Big Bang, were both anticipated and identified. Despite their significance, all these findings have overlooked the predominant kind of matter in the universe. In 1970, a finding rekindled interest in dark matter, leading to such an increase in focus that by the late 1980s, astronomers globally were performing comprehensive investigations of dark matter within individual galaxies. While Oort proposed that dark matter resides within the disks of galaxies, Ken Freeman and colleagues utilized radio telescope observations to assess galactic rotation, uncovering the initial evidence that dark matter exists in extensive halos enveloping the centers of galaxies, including the Milky Way. Oort, Lindblad, and Stromberg elucidated the Milky Way's rotation by examining stellar motions. Oort's subsequent measurements of stellar motions perpendicular to the galactic disk enabled him to ascertain the galaxy's mass, culminating in what is today seen as the fallacious conclusion that the disk of our galaxy harbors dark matter. What is the status of other galaxies? What is their mass, and do they encompass dark matter? Other galaxies are so far that their star clusters manifest as indistinct patches of light to all but the most powerful telescopes, rendering it unfeasible to ascertain their mass by observing individual stars. An alternative is required. If it is a spiral galaxy, the process is rather simple. As all the stars rotate collectively, one can measure the galaxy's rotation speed and compute the requisite gravitational mass to maintain its cohesion. In 1939, Horace Babcock endeavored to accomplish this for the Andromeda galaxy, designated Galaxy M31. He quantified the Doppler changes at multiple locations throughout the galaxy's periphery, and subsequently contrasted these with the galaxy's mean spatial movement to ascertain the rotating velocity. However, translating the perceived velocity of a galaxy's edges into kinetic energy necessitates understanding the galaxy's actual dimensions, which are contingent upon distance and apparent size. Calculating luminous matter requires knowledge of the galaxy's brightness, contingent upon its distance. During Babcock's observations, the distance to M31 was inadequately understood. Ultimately, he miscalculated its distance and dimensions, concluding that the ratio of luminous mass to gravitational mass was 50. Although this is now recognized as incorrect, he was at least progressing in the correct direction. Babcock and his contemporaries were confined to observing solely the visible disks of galaxies. Nevertheless, the dark matter issue soon transcended this limitation. Observing the universe at alternative wavelengths proved unfeasible. Hence, all observations employed optical spectral line shifting. Oort significantly contributed to the advancement of Dutch radio astronomy. Notably, one of his students, Henk van der Hulst, predicted the existence of the 21 cm line of neutral hydrogen, which was discovered in 1951. This radio emission resembles the spectral lines of Oort and Zwicky, but originates from neutral hydrogen gas interstellar, rather than from stars. The electromagnetic spectrum, encompassing radio and visual bands, conforms to identical physical rules. Consequently, spectral lines in the radio spectrum undergo identical Doppler changes resulting from motion along the line of sight. The production of the 21 cm spectral line by hydrogen gas within and surrounding a galaxy, rather than by stars, is a significant advantage. It allows radio astronomers to quantify the Doppler shift and, consequently, the movements of various regions within a galaxy, irrespective of the presence of stars, provided that hydrogen gas exists in its neutral or atomic state. We conduct this study using devices such as the Australia Telescope Compact Array. A hydrogen map of the galaxy captures the Doppler shifts of radio waves emitted from various locations within the galaxy, enabling the measurement of highly accurate velocities across a hydrogen-rich galaxy. Galaxies that exhibit visible hydrogen are predominantly spiral or irregular in shape. If galaxies possess no additional complexities beyond their visible attributes, the stars and, crucially, the gas in the peripheral regions of a galaxy would exhibit slower velocities than the stars situated nearer to the center. This is due to the diminished gravitational force at greater distances from the galactic core, necessitating less rapid motion to counteract the inward gravitational attraction. A graph depicting the galaxy's rotational velocity about its distance from the center is called a rotation curve. Without the influence of dark matter, a galaxy's rotation curve is expected to ascend to a maximum and subsequently decline, signifying that the rotational velocity decreases as one moves outward toward the galaxy's periphery. Oort identified the asymmetrical rotation of our galaxy in the 1930s. It was universally accepted that the rotation curves of galaxies contained no unexpected findings. Optical techniques quantified numerous rotation curves in the 1960s, examining the ionized gas in the central regions of spiral galaxies. Nonetheless, these rotation patterns do not extend to the galaxy's peripheral regions. In fact, no significant revelations emerged until the 21 centimeters data became available. During the investigation of an unrelated subject, Freeman uncovered that galaxies were not rotating as previously presumed. Spiral galaxies exhibit a distinctive light distribution, with luminosity decreasing exponentially from the center to the periphery, the rationale for which remains unknown. Freeman analytically computed the rotation curve for the galaxy and juxtaposed it with the known rotation data. The measurement of galaxy rotation curves is limited to the extent of hydrogen gas, which usually extends well beyond the observable boundary. Upon reaching the conclusion of the rotation data, we may quantify the mass within the final measurable radius. In 1970, despite limited observations of the rotation of other galaxies, Freeman uncovered sufficient evidence to ignite his interest. He observed that the rotation curves of 3 or 4 galaxies exhibited an incorrect form, predicated on the assumption that the galaxies comprised solely stars and gas. Their alignment with the anticipated curves was inadequate, since the observed rotation curves deviated from expectations. This indicates that stars and gas are not approaching the center, but are occasionally moving at greater velocities. Freeman published an article indicating that there was unequivocally an issue. The apparent reason he proposed was that these galaxies harbored considerably more dark matter than luminous matter. However, this was not observed in the disks. It had to exist beyond the stars and gas, enveloped in a halo of dark matter that entirely encircled the radiant galaxies. Recent 21 cm scans of the Andromeda galaxy, conducted by teams in the UK and US, simultaneously corroborated the notion that an anomaly existed. Shortly after Freeman's announcement, another concept stimulated astronomers' contemplation. This notion, akin to Oort's research, is considered less pertinent to the dark matter conundrum. Yet it initially encouraged astronomers to contemplate dark matter earnestly. In Film 3, we noted that Hubble categorized galaxies according to their morphology. Around 1/3 of the spirals were estimated to exhibit prominent central bars, known as barred spirals. In 1973, Princeton University astronomers Jeremy Ostraker and James Peebles presented a paper elucidating the scarcity of bar formation in spiral galaxies. What factors inhibited the majority of galaxies from forming bars? During that period, individuals initiated computer simulations of spiral galaxies and observed that their models frequently developed central bars. Stars congregate due to their mutual gravitational attraction, and their sociable disposition is infectious. A minor aggregation of stars will induce further clumping, drawing additional stars and perpetuating the process. The clumps form due to gravitational instability, which propels the galaxy into a bar shape, as this configuration is more stable than a uniformly distributed disk of stars. At that time, astronomers were unaware that around 2/3 of spiral galaxies possess bars, prompting inquiries on the absence of bars in the other spirals. Ostraker and Peebles contended that a substantial halo of dark matter surrounding a spiral galaxy could inhibit the formation of a bar, as they believed that most spirals lacked bars. This would diminish the gravitational influence of the stars on the galaxy's morphology. The stars would serve as test particles, delineating the shape dictated by the dark halo. We now recognize alternative methods to inhibit bar development. One method involves augmenting the random motions of stars within the inner regions of the disk, disrupting their orderly circular trajectories, and enhancing the chaotic movements of stars toward the center. During the 1980s, Freeman and his colleagues at Mount Stromlo Observatory and the University of Groningen measured the random motions of stars in the disks of several spiral galaxies, including our own galaxy. Since that time, astronomers have conducted analogous measurements of additional spiral galaxies. The outcome indicates that velocity dispersion, the degree of randomness, is significantly elevated in the centers of galaxies, stabilizing them against forming a bar structure. It is currently understood that in most galaxies, the black halo plays a crucial role in the structure and dynamics of the outer regions. whereas the interior regions are mostly governed by the gravitational effects of stars. Oestreicher and Peebles accurately deduced that dark matter halos encircle galaxies, though perhaps not for the reasons they initially proposed. While arriving at the truth may appear chaotic or unstructured, it consistently occurs in science. The 1970s were a pivotal era for the advancement of dark matter research. Building upon their concepts of dark halos, Oestreicher and Peebles, alongside their associate Amos Yahil, compiled the dynamical evidence accessible at that time concerning the masses of galaxies. This prompted the belief that massive spirals, such as our galaxy, possess galaxies with approximately 10-12 solar masses, significantly greater than previously assumed. They utilized the neutral hydrogen rotation curves of three proximate spiral galaxies, M31, M81, and M101, as measured by Morton Roberts and Arnold Rotz, as evidence. They examined galaxy pairs' motion and determined tiny galaxy clusters' virial weights. Their study, published in 1974, included fundamental data that significantly advanced our understanding of dark halos surrounding galaxies. Their mass estimations approximate the most accurate figures attainable today, 3 decades later. As is frequently observed in scientific discourse, their conclusions coincide with those of others. In Estonia, Einasto and his colleagues, Karsik and Saar, similarly deduced that spiral galaxies must possess significant mass in the same year. In the 1970s, Vera Rubin and her associates at the Carnegie Institution of Washington gathered high-quality optical rotation curves for spiral galaxies, which typically exhibited flat rotation curves. Although flat optical rotation curves seldom yield definitive evidence for dark matter, as they do not extend sufficiently from the galaxy's center, these data have perpetuated discourse on the issue. Nonetheless, the definitive evidence occurred in 1978 when Albert Bosma submitted a PhD thesis at the Kaptein Laboratory in Groningen. He produced 21-centimeter rotation curves for approximately 20 spiral galaxies utilizing the Westerbork radiosynthesis telescope, illustrating that virtually all were situated at the periphery of the 21-centimeter data. By the conclusion of the 1970s, it became evident that a significant issue existed. Either the Newtonian formulation of gravity is erroneous, a notion some consider seriously, as will be discussed later, or galaxies are encircled by massive dark matter halos. However, the issue may be more substantial. The rotation curves obtained from 21-centimeter emissions reveal the galaxy's rotational velocity up to the extent of the hydrogen gas. The likelihood of identifying additional mass remains substantial, as it exists beyond the observable boundary of hydrogen. Consequently, the inquiries persist. What is the extent to which we can investigate the dark matter? Halo. Is there a method to investigate beyond the hydrogen disk of a galaxy? Analyzing the hydrogen distribution in spirals uncovers a pronounced edge. The density of hydrogen progressively diminishes over distances spanning several kiloparsecs before abruptly vanishing at the final kiloparsec. This occurs due to the absence of hydrogen, although it is merely that humans cannot see it. What is the reason for the hydrogen's abrupt invisibility? Likely due to ionization by UV rays. When an ultraviolet photon interacts with a hydrogen atom, it dissociates the positive nucleus, a solitary proton, from the negative electron. The source of this UV radiation remains enigmatic. However, two distinct theories exist. Quasars in outer space emit significant UV light. However, stringent constraints on their production render this an incorrect response. Another option is that the majority of spiral galaxies in their central regions exhibit significant star formation, resulting in substantial UV radiation emission. In what manner do the star-forming regions at a galaxy's core affect the hydrogen in its peripheral areas? Galaxies are predominantly flat, and in hydrogalaxy, the outer portions cannot directly observe the star-forming regions at the center because of the substantial dust in the inner areas that absorbs UV radiation. Notwithstanding the ostensibly planar configuration of galaxies, the peripheral areas are typically not entirely flat, as the hydrogen disk frequently exhibits warping, resulting in a shape reminiscent of the brim of a slouch hat. Jos Bland Hawthorne of the Anglo-Australian Observatory noted that this provides hydrogen in the galaxy's periphery, with a more direct view of the core regions where star formation occurs. This galaxy has been recognized for 25 years, and while warping of the star plane is infrequent, warping of the hydrogen layer is prevalent. It is now understood that most galaxies exhibit warping. Despite the existence of several ideas concerning the origin of these warps, the rationale for their presence remains obscure. The dark matter halo may exhibit a favored plane of symmetry owing to its marginal flattening. If this plane is not parallel to the galactic plane of stars, it will exert a gravitational influence, attracting the hydrogen in its outer regions toward itself, above the stellar plane, where the dark galaxy is elevated, and below, where it is depressed. Nonetheless, it persists as a quintessential dynamical conundrum in astronomy, and despite the efforts of some of the most brilliant intellects, it remains unsolved. The hypothesis that hydrogen aligns with the star-forming areas in the galaxy's center is quantitatively more effective than certain explanations of the galaxy. Nonetheless, this is very novel, and perspectives will undergo numerous transformations. One can question why only the outer areas of the galaxy undergo this ionization. What is the reason for the lack of ionization in the remainder of the visible disk of the hydrogen galaxy? The entire galaxy is subjected to a dose of Alt-Galaxiette radiation emanating from the core, yet the galaxia-violet photons can only ionize to a limited extent before depletion occurs. If an area has abundant hydrogen, the ionizing photons are consumed in the upper layer of hydrogen. The internal hydrogen remains neutral and is observable due to its protection from ultraviolet light. In the farthest regions of the galaxy, when hydrogen density is significantly diminished, a threshold is attained where ultraviolet photons may ionize practically all hydrogen and maintain this state. When this transpires, the observable neutral hydrogen in the 21 cm line sharply diminishes. This could explain the sharp appearance of the edge. Nevertheless, it also indicates the presence of an area of ionized hydrogen beyond the neutral hydrogen boundary, observed with radio telescopes. An ionized hydrogen atom experiences recombination to sustain its ionization over time. When an ion, namely a hydrogen nucleus or proton, encounters an electron, they combine and generate recombination radiation. An additional UV photon rapidly ionizes this neutral hydrogen atom. This recombination radiation can be observed as a series of spectral lines. Among these lines, amateur and professional astronomers notably recognize the H-alpha line as the most prominent hydrogen line observable from Earth. The H-alpha radiation, emanating from the peripheral regions of galaxies, is exceedingly faint, and until recently, it was undetectable. Astronomers can now quantify these minimal quantities of ionized hydrogen emission due to spectrograph advancements and a Fabry-Perot interferometer device. Freeman, alongside Jos Bland Hawthorne and other colleagues, has conducted observations using the 3.9-metre Anglo-Australian telescope at Siding Spring Observatory in New South Wales. They have extended the rotation curves beyond the constraints previously established by neutral hydrogen. The initial galaxy on which this technique was employed was the prominent proximate spiral NGC 253, and the methodology has since been applied to M33, a renowned spiral galaxy adjacent to the Andromeda galaxy. The degree of hydrogen's expansion dictates the boundaries of this approach. The direct observation of the dark matter halo remains distant. We can further extend our observations beyond the atomic hydrogen threshold by utilizing satellite galaxies as indicators of the gravitational field. The erratic trajectories of these satellites orbiting their host galaxy inhibit their descent into the parent galaxy, allowing us to utilize their movements to assess the gravitational field of the galaxy up to several hundred kiloparsecs from its center. Dennis Zeritsky of the Galaxies Observatory innovated this approach. The black halos of spiral galaxies, including ours, extend to 150 kiloparsecs. Having addressed spirals, what can be said regarding the colossal elliptical galaxies? Astronomers have inferred the presence of dark matter halos by analyzing the rotation curves of spirals. The movements of stars in elliptical galaxies are not entirely simple. What methods are employed to ascertain the mass of inactive, non-rotating galaxies? Numerous methods exist for determining the masses of elliptical galaxies, and while none are as straightforward as those used for spiral galaxies, two methods are particularly notable. One method involves examining the movements of distant objects within the halos of elliptical galaxies, such as planetary nebulae or globular clusters, whose velocities may be individually quantified. Planetary nebulae are significant in the quest for dark matter, warranting a thorough examination of these exquisite entities. We have observed how big stars conclude their short yet luminous lives in dramatic supernova explosions. Nevertheless, such stars are rare. Most stars conclude their existence as serenely as they commenced. Billions of years after their formation in immense clouds of gas and dust, stars such as the Sun expire tranquility, enveloped by ethereal clouds that emit a quiet glow in the cosmos. For a cosmologically fleeting moment, these exquisite clouds in the sky impart knowledge to scientists on the future existence of sun-like stars. The comprehension of stellar mortality commenced in the 17th century as astronomers explored the cosmos, utilizing a new era of huge telescopes. Conceived in the early 16th century, telescopes possessed diminutive lenses until the mid-17th century, which only disclosed the closest and most luminous celestial bodies in the nocturnal sky. William Herschel was among the astronomical pioneers. Herschel was a proficient guitarist. Nonetheless, his genuine interest lay in astronomy. Using a handcrafted telescope, he surveyed the skies for novel, unexplored celestial bodies. In 1781, he discovered Uranus, the first planet identified since ancient times, whose irregular movements ultimately resulted in the discovery of Neptune and served as one of the initial instances of detecting unknown dark matter through the behavior of observable matter. Astronomers frequently saw small spherical gas clouds that resembled planets while surveying the cosmos. When observed through 18th century telescopes, the appearance of these peculiar objects may deceive an astronomer into believing they had identified a new planet or comet. Meticulously monitoring the suspect was the sole method to validate the identification of a planet. Planets revolve around the Sun and shift against the backdrop of stars from one night to the next. Conversely, the nebulae remain stationary relative to the stars. Due to the superficial similarity of certain nebulae to planets, Herschel designated them as planetary nebulae. They captivated him, and upon discovering one with a dim star at its core, he became convinced that the nebulae were gaseous clouds encircling a star. This was a significant revelation given the limited understanding of stars at that time, which was nearly non-existent. 2 centuries later, astronomers have validated Herschel's depiction. A planetary nebula is a gaseous cloud encircling a star nearing the conclusion of its life cycle. All stars, including the Sun, generate energy through nuclear fusion, mostly converting hydrogen into helium. The nuclear process generates vast amounts of energy, a portion reaching Earth as light and heat. The external expulsion of energy produced in the star's core sufficiently counterbalances its immense gravitational force, maintaining its expansion for billions of years. Nevertheless, the limited availability of hydrogen fuel constrains a star's lifespan. Approximately 5 billion years after its formation, a star such as the Sun experiences a depletion of its hydrogen reserves. As the star emits diminished energy, its core undergoes contraction due to gravitational forces. The heightened density near the core amplifies the star's energy output, expanding and cooling the outer layers. The star expands to several tens of times larger than the Sun's diameter, becoming a red giant that outshines the Sun by a factor of 100. The density escalation at the core is sufficient to initiate the fusion of helium into oxygen and carbon, while the transformation of hydrogen into helium persists in a shell surrounding the core. The star resembles an egg, a helium yolk encircled by white hydrogen. The star ultimately depletes its helium. However, its mass inhibits the combustion of oxygen and carbon, which generates heavier elements. Without outward rushing energy to sustain the star's expansion, its core succumbs to gravitational collapse. Once more, the outer layers expand and cool, yet the star increases to several hundred times its initial diameter in this instance. At the center of the inflated star is the expiring core, comprising half the mass of the Sun, and currently 1,000 times more luminous. A fragile stream of matter from the core moves at up to 20 km/s velocities. The growing gas cloud, formerly the star's outer layers, escapes the gravitational pull of the core and wanders softly into space. As the gas spreads, it cools, becoming frigid and obscuring the star within. After millennia, the core ultimately collapses, reaching temperatures of approximately 25,000 K. The immense radiation from the star causes the surrounding gas to illuminate, similar to how gas in fluorescent tube lights when subjected to electrical current. At its zenith, the central star can attain a temperature of 200,000 K, equivalent in luminosity to 1,000 suns. The luminous gas has transformed into a planetary nebula with a blazing center star, and may endure for 100,000 years. Ultimately, the gas dissipates, and the star ceases to exist as a white dwarf. Despite their splendor, planetary nebulae are merely ephemeral formations in the cosmos. A typical planetary nebula may contain up to 100,000 atoms within the volume of a sugar cube. In comparison, the air you inhale has approximately 10 quintillion atoms inside the same volume. The cloud is so tenuous that variations in mass distribution within the star or the density of the surrounding interstellar medium can induce it to assume unusual shapes. Although most planetary nebulae exhibit symmetry, only approximately 10% seem spherical. Planetary nebulae briefly exist, and their gaseous remnants disperse within tens of thousands of years. Nevertheless, their distinctive trait renders them conspicuous amidst the surrounding darkness. The physics in the gas surrounding the hot central star indicates that approximately 20% of the star's light is emitted at a specific wavelength and manifested as a prominent emission line. This spectral line resulted from doubly ionized oxygen, (O4eus), at a wavelength of 5007 angstroms in the blue region, green segment of the visible spectrum. This signifies that the luminosity of these little stars at this specific wavelength exceeds that of their environment. Planetary nebulae serve as indicators for the matter in adjacent elliptical galaxies. Globular clusters offer an alternative to planetary nebulae, exhibiting sufficient brightness to be detected in proximate elliptical galaxies. Nonetheless, big telescopes are necessary for this observation. Extensive dark matter seemingly envelops elliptical galaxies, a subject of investigation. These strategies inherently rely on an assumption of stellar motion, which remains uncertain. With the spirals, we understand that all is revolving in cycles, which renders. Life appears uncomplicated, but regarding ellipticals, the nature of such movements remains unclear. An alternative independent method leverages the phenomenon that numerous elliptical galaxies generate X-rays from heated gas in their peripheral areas. This gas is not in rotation. It is only a chaotic disarray. Astronomers suggest this phenomenon occurs due to aging stars in other galaxies emitting gas. The gas, propelled by its velocity, is ejected into the interstellar medium, creating clouds that traverse various trajectories and collide with gas from other stars moving in opposing directions. The energy previously contained in the gas's motion is transformed into heat, sufficient heat, in fact, to generate X-rays. Elliptical galaxies are frequently luminous in X-rays, allowing for the examination of the distribution of this hot gas and the determination of the gravitational field required to keep it. A substantial number of the elliptical galaxies examined in this manner are the prominent central galaxies located at the cores of clusters. M87 in the Virgo cluster and NGC 1399 in the Fornax cluster are supergiant elliptical galaxies, readily measurable due to their abundant X-ray emissions, globular clusters, and planetary nebulae. Although neither approach, analyzing the distribution of hot gas, nor examining the dynamics of globular clusters and planetary nebulae, is definitive, both produce consistent outcomes. The morphology of dark matter halos continues to be enigmatic. They may be round or compressed, resembling a partially inflated beach ball. The sole certainty is the quantity of mass contained within a specified radius. The problem is intriguing, since simulations conducted by astronomers of the early universe's formation and halo dynamics consistently yield flat halos. The normal halo is predominantly prolate, resembling a rugby ball to a minor extent. Thus far, validating the idea by observation has been exceedingly challenging. Freeman has participated in such endeavors and can attest that it is a discouraging process. One of the initial endeavors to quantify the configuration of the dark matter halo entailed investigations of polar ring galaxies. These atypical galaxies have a standard disk galaxy surrounded by a ring of stars and gas that rotates in a plane orthogonal to the disk. Currently, 157 polar ring galaxies have been identified, and while their formation process is still enigmatic, they may arise from the merger of two conventional galaxies. The disk of the primary galaxy is relatively recognizable, albeit nearly entirely devoid of the gas necessary for galaxy formation. Star formation transpires in the orthogonal ring, occasionally comprising several billion solar masses of neutral hydrogen. In 1983, Vera Rubin, Francois Schweitzer, and Brad Whitmore released a significant work analyzing the velocities of matter in the polar ring of the galaxy AO 136 08Jo1. Similar to the galaxy disk, the rotation curve of the galactic ring was flat, leading to the conclusion that galaxies are enveloped by dark matter that extends at least 3 times beyond the apparent boundary of the galaxy. A notable instance of this occurrence is the galaxy pair NGC 46 Fit A. This entity comprises 2 galaxies colliding, resembling 2 massive perpendicular wheels with a shared center. Astronomers anticipated that the existence of 2 concentric galaxies with disks oriented in opposing planes would elucidate the configuration of the dark matter halo enveloping them. Freeman was among them. The objective was to quantify the rotation rates of galaxies in 2 orthogonal planes, therefore elucidating the forces in those dimensions and, consequently, the quantity of dark matter in those orientations. Notwithstanding original expectations, the outcomes remain equivocal. And even with more recent and significantly enhanced data, accurate interpretation continues to provide challenges. The rationale is that various methods exist to replicate what is observed. As demonstrated by Magda Arnaboldi and Françoise Combe, certain theories provide a flat dark matter halo, which may orient in one plane or another, rendering it challenging to ascertain the accurate explanation. Flaring of the hydrogen disk. A further method astronomers employ to ascertain the configuration of dark matter halos involves examining the hydrogen flaring within the disks of galaxies. The hydrogen layer in a galaxy is not perfectly planar. The central areas are flat, whereas the peripheral sections expand outward, resulting in increased thickness, presumably due to the disk's reduced mass and gravitational influence. Consequently, the hydrogen layer thickens in the outer parts of the galaxy. The extent of flattening is significantly influenced by the configuration of the dark matter halo. The halo of a flat galaxy has a greater gravitational influence on hydrogen, drawing it towards the disk more effectively than a spherical galaxy. Astronomers have sought to make arguments based on the quantity of hydrogen at different distances from the galactic center. Initially, this technique appeared promising. Nonetheless, it has provided multiple solutions. Consequently, astronomers possess a considerable advantage in comprehending the configuration of the dark matter halo. It would be gratifying to confirm the accuracy of the cosmological models. The interpretation of Project Maca's results, one of the most ambitious dark matter searches, hinges on the configuration of the dark matter halo, presenting a significant practical concern. Until then, we must acknowledge the existence of dark matter halos and their influence over galaxies. Astronomers have measured the dark matter halos of many galaxies, indicating that dark matter is present in all galaxies. Ours is not an exception. Despite Oort's first observations, the dark matter of the Milky Way is not situated within the disk. Rather, it exists in a halo akin to that of other galaxies, a fact that would be more agreeable to several astronomers. What is the basis of our knowledge? The Sun is approximately 8 kiloparsecs from the center of the galaxy, and up to about 20 kiloparsecs. Analogous rotational procedures employed for other galaxies can produce comparable outcomes. The rotation curve remains constant at this distance, indicating the presence of a dark matter halo. A preliminary association between mass and distance from the galactic center is observed. Mass equals 10 billion solar masses, multiplied by the radius in kiloparsecs. Galaxy employs the British billion, equivalent to 1,000 million. Consequently, when attaining a radius of 20 kiloparsecs, we estimate approximately 200 billion solar masses inside a diameter of 40 kiloparsecs. Almost threefold the amount we can attribute to starlight. In summary, we are already much advanced in the presence of dark matter within the Milky Way. Nevertheless, we face an obstacle beyond approximately 20 kiloparsecs. Due to the rotation of the galaxy, all objects observed beyond the Sun's orbit are traversing our line of sight, with negligible components along that line. Doppler shift measurements of star motions are largely ineffective in this context, necessitating exploring alternative approaches for quantifying the Milky Way. Instead of lamenting our existence within the galaxy, astronomers capitalize on it. We seek indicators beyond the 20 kiloparsec galaxy that will elucidate the movement of matter, and consequently, the mass, surrounding the Milky Way. What exists beyond? This constitutes the star halo of the galaxy. This should not be conflated with the dark matter halo, but rather with the galaxy's weak luminous halo, which encompasses some of the galaxy's oldest stars. However, one need not search extensively within the halo for halo stars, as a handful are readily accessible to us. The stars in proximity to the Sun are part of the galactic disk and are orbiting the galaxy alongside us. However, a minority of stars, approximately 1 in 1,000, originate from the galaxy. The bright halo is a nearly spherical star collection with minimal rotation. Rotation preserves the disk, while the erratic movements of the stars within the bright halo maintain its structure. The dynamic and vigorous halo stars traverse the galaxy with B's energy. Due to these erratic movements, certain stars will inevitably traverse the vicinity of the Sun by coincidence. They traverse swiftly. This elucidates the advantages of ascertaining the gravitational mass of the galaxy. To ascertain the mass of the Milky Way, one must measure the velocity of the rapidly moving galaxy traversing the solar vicinity, and compute the requisite mass to maintain its gravitational binding to the system. This is referred to as the escape velocity argument, as it is predicated on the premise that if these stars had attained the galaxy's escape velocity, the speed required to overcome the gravitational pull of the Milky Way, they would have already departed. The gravity of the Milky Way ensnares them, as demonstrated by their rapid movement and closeness. What if the star is an intruder, not a constituent of the Milky Way? This is indeed a possibility. Stars are present in the intergalactic space, as will be demonstrated later in our investigation of dark matter's nature. Nonetheless, we must recognize that if a star moves through the solar vicinity within the galaxy's disk, it is highly probable that it belongs to the galaxy. Nevertheless, the escape velocity establishes a minimum threshold for the galaxy's mass. Despite the tremendous velocity of galaxy stars, it may still be considerably less than the galaxy's escape velocity. While stars, traveling at velocities of approximately 650 km/s, are recorded traversing the Milky Way neighborhood, to evade the gravitational influence of the Milky Way, a star must attain speeds of 800–900 km/s. However, such stars have either not been detected or may not exist. Another theory is that hot stars from galaxies never traverse the solar vicinity. Thus, the escape velocity argument may provide a lower limit for each of those galaxies. However, the lower threshold is approximately 300 billion solar masses, representing a 50% augmentation of the mass of the galaxy, as established by the rotation curves. Objective prism unveils halo stars. What methods were employed to initially discover galaxy halo stars on Earth? How can we distinguish them from the disk stars? Fortunately, there are several methods available. One should seek out proximate luminous halo stars, which is quite evident, especially when examining colder stars. The ancient halo stars originated before the galaxy's enrichment, with heavy elements produced in supernova explosions. Consequently, they possess distinct chemical properties. Specifically, they are metal poor, indicating that their heavy element abundances, calcium, magnesium, and iron, are less than 1/10 of those in the Sun. Astronomers began analyzing several stellar spectra, seeking those with exceedingly faint spectral lines. This task is less difficult than it appears. A Schmidt telescope enables astronomers to capture the spectra of several stars simultaneously. Schmidt telescopes are unusual, frequently conical instruments featuring a sky-end aperture smaller than the primary mirror. Nonetheless, their optical configuration enables the production of clear images across an extensive field of view. Consequently, they are optimal for doing all-sky surveys within relatively brief durations. We have previously observed how starlight can be dispersed into a spectrum to disclose its spectral lines, often accomplished using a spectrograph. A more efficient method involves using a glass prism that attaches to the front of the telescope to locate a rare type of star. These objective prisms are colossal. A Schmidt telescope, like the United Kingdom Schmidt telescope at the Anglo-Australian Observatory, would be utilized, with a 48-inch diameter prism, positioned at the front of the telescope. The objective prism disperses incoming starlight before its contact with the film, resulting in a photograph that displays the minute spectra of several stars, with each spectrum indicating the chemical makeup of a star. The resultant shot employs various approaches to differentiate between metal-rich and metal-poor stars. One approach is to examine the spectra. Numerous astronomers have undertaken this analysis. Overlay a grid over the shot to ensure no stars are overlooked, and meticulously analyze each spectrum sequentially in search of metal-poor stars. A contemporary method involves utilizing computerized measurement devices to identify and evaluate the spectra on the photographic plate. Astronomers employ a larger telescope to obtain a more detailed spectrum to confirm its characteristics upon identifying a metal-poor candidate star. Regrettably, halo stars are exceedingly rare, and astronomers have identified numerous objects that do not constitute the elusive targets they pursue. Automation has significantly simplified the work, and although this modernization was overdue, it was propelled by astronomers' profound interest in metal-poor stars. Another method for identifying halo stars leverages their rapid motion. The motion of a star across our line of sight is referred to as its proper motion, as detailed in Film 1. This can be quantified by capturing two images of the same stars at the maximum temporal interval feasible, or, more pragmatically, by contrasting a contemporary photograph with one taken significantly earlier, typically by another individual. Analyzing the relative locations of the stars indicates rapid stellar motion. The greater the velocity of a star across the celestial plane, the more it will have displaced between the two captured images. Certain halo stars exhibit apparent movements in the sky of 0.5 arcseconds per year or greater. This may appear to be a negligible quantity. It is less than 3,500 times smaller than the diameter of the full moon, but it is not challenging to quantify. The movement is substantial in the broader context, resulting from their rapid traversal through space. A seemingly fast-moving star suggests one of two possibilities. Either in proximity, the nearer a star, the swifter its apparent motion across the sky, or traversing space at a high velocity. If it is the latter, it may be a halo star deserving of further examination. Frustrated by the delay in the observational emergence of halo stars in the solar vicinity, certain astronomers investigated the luminous halo directly. The methodology is identical to that employed in the search for proximate, metal-poor stars. However, one fundamental factor complicates the search for halo stars within the halo: their considerable distance and extreme faintness. Nevertheless, astronomers have identified them at distances of 100 kiloparsecs. Astronomers can ascertain the galaxy's mass and the dark matter ratio by analyzing its stochastic motions. Astronomers analyze stellar pressure in the galaxy's outer regions, which offers insight into the total mass. It encompasses around 500 billion solar masses, within an average radius of about 50 kiloparsecs. The rotational considerations dictate up to 2.5 times the mass. Outside our galaxy exists another valuable instrument for determining the overall mass of the Milky Way, the Andromeda Galaxy. This remarkable galaxy, the largest in the local group, is a spiral distinct from ours. It is approximately 750 kiloparsecs away and is the closest substantial galaxy to the Milky Way. Due to its inclination of around 15 degrees from edge-on, it appears as an oval-shaped hazy light in the northern constellation of Andromeda. We are truly privileged to observe such a spectacle with our unaided vision. The Andromeda Galaxy and the Milky Way converge at approximately 118 kilometers per second. This is atypical, as the bulk of galaxies are receding from us, influenced by the expansion of the universe. What is causing the Andromeda Galaxy and the Milky Way to converge? The solution is gravity, signifying the presence of substantial matter. The two galaxies likely originated simultaneously, alongside numerous smaller galaxies that constitute the local group. Although Andromeda and the Milky Way first diverged due to the universe's expansion, their mutual gravitational attraction was adequate to cease and subsequently reverse this divergence. This monumental task necessitates ascertaining the total mass between the two galaxies. In 1959, English astronomer Frans Kahn and Dutch astronomer Lodewijk Voltier, a pupil of Oort, developed this approach. The term timing argument is used since it necessitates an assumption regarding the duration required for the two galaxies to counteract universal expansion and commence their approach towards one another. We must postulate an age for the universe. If the cosmos is ancient, space has sufficient time to rotate and aggregate galaxies. This implies that mitigating the recession necessitated reduced mass. Conversely, if the universe is youthful, there has been insufficient time to accomplish the same outcome, necessitating that galaxies be more massive to coalesce within a significantly reduced time frame. Although Kahn and Voltier were still striving to determine the exact age of the universe, we may ballpark it at around 18 billion years for illustrative purposes. This is somewhat lengthy. The now recognized age is 13.7 billion years, therefore providing a conservative estimate of the entire mass of the two galaxies. The total mass of the two galaxies is 4,000 billion solar masses at this age. Our portion is under 50%, approximately 1,500 billion solar masses. This is approximately 8 times the mass derived from rotation curves and 15 times the mass suggested by the galaxy's bright stuff. Comparable arguments can be applied to smaller galaxies approaching us, resulting in unexpectedly analogous outcomes. These factors instill trust in astronomers regarding their studies on dark matter in the Milky Way. A mass of 1,500 billion solar masses indicates that the flat rotation curve of the galaxy should stretch beyond 100 kiloparsecs. This is not unexpected, considering the brilliant stellar halo reaches this distance, making it plausible that the dark matter halo extends similarly. When all these arguments are synthesized, they establish a correlation between radius and mass previously referenced. For our galaxy, the galactic mass is equivalent to its radius in kiloparsecs multiplied by 10 billion solar masses, and this correlation persists up to at least 100 kiloparsecs. In this regard, we possess significantly greater knowledge of our galaxy than any other galaxy, mostly due to our unique position, enabling us to utilize additional arguments. In most galaxies, the process concludes once hydrogen is depleted to assess rotation curves. The projections cease. The ratio of the dark mass of our galaxy to the luminous mass is at least 20-fold. However, the examination of typical spirals, like our galaxy, yields far smaller figures, primarily because of the incomplete measurement of mass once the hydrogen is depleted. Hydrogen extends beyond the stars, yet galaxies reach significantly further. The measured rotation curves of normal spiral galaxies indicate a dark matter to luminous matter ratio, ranging from 1.1 to 5:1, with just a few exceptional instances approaching the ratio observed in the Milky Way. Consequently, the Milky Way is a more accurate portrayal of the circumstances of numerous galaxies. Smaller spinning galaxies have analogous outcomes, suggesting that galaxies' actual dark matter to light matter ratio is less than 20.1. In recent years, astronomers have utilized a neighboring galaxy to ascertain the ratio of dark matter in the Milky Way merely sufficient. Astronomers have ascertained the real spatial velocity by analyzing the transverse motion of the Large Magellanic Cloud and correlating it with their established understanding of motion along our line of sight. This in itself does not disclose any information regarding the mass of the Milky Way. However, an additional component now comes into play. the large and small Magellanic Clouds interact. The Milky Way's two largest satellite galaxies, the Magellanic Clouds, appear to be orbiting their massive spiral counterpart in a tranquil manner. These large, luminous and exquisite galaxies adorn the dark southern skies, enhancing the radiant arc of the Milky Way. Nonetheless, their tranquil facade masks a deluge of violence as their closeness to the Milky Way gradually annihilates them. Evidence of their gradual yet inescapable decline is a trail of hydrogen remnants indicating their trajectory. The Magellanic Stream spans tens of thousands of light-years in space, creating a vast arc that covers almost 100 degrees in the celestial sphere. The Magellanic Stream, named as such, was identified in 1976 by Australian astronomer Don Matthewson, the former director of Mount Stromlo and Siding Spring observatories. Matthewson discovered a vast stream of neutral hydrogen gas trailing behind the two clouds, resembling the smoke from a burning vessel. The revelation of a substantial volume of gas escaping from the two galaxies has significant implications. The Magellanic Clouds were, in a manner, perishing. A galaxy utilizes hydrogen gas as its nutrient source to generate stars which bestow luminosity upon the galaxy. However, stars are not eternal and require replenishment. So if a galaxy's gas reservoir is depleted, no material will be available to form new stars. The Magellanic Stream represents the loss of gas from the clouds, leading to the starvation of the galaxies. While the Magellanic Stream evidently signifies the obliteration of the Magellanic Clouds, the precise mechanism underlying this phenomenon remains ambiguous. According to tidal theories, one hypothesis posits that the stream is a consequence of a tidal interaction wherein the immense gravitational force of the Milky Way is extracting material from the Magellanic Clouds. An alternative hypothesis is referred to as ram pressure stripping. The concept posits that the stream is generated as the clouds traverse the sparse gas enveloping the galaxy's halo, collecting gas from the clouds akin to long hair in the wind. The halo gas creates a heated corona that envelops the galaxy to a distance of no less than 70 kiloparsecs, and can be directly observed through the analysis of the X-ray spectra of quasars. Until recently, it was challenging for most astronomers to ascertain which theory was accurate. A significant advancement in 1998 nearly validated the tidal theory about the origins of the Magellanic Stream. The discovery occurred during HIPAS, the H.I. Parkes All-Sky Survey. This study examines the entire southern sky for large-scale structures beyond our galaxy, utilizing the 64-meter Parkes radio telescope and the specialized Parkes multi-beam facility. This endeavor is exceptional due to the substantial monitoring time required. Surveying the sky point by point with a single radio telescope and receiver would have required an extensive period. The Parkes telescope typically observes a limited portion of the sky, approximately 1/4 the size of the full moon, rendering an all-sky survey such as HIPAS a task that would have previously required 30 years. The Parkes multi-beam facility irrevocably altered the situation. Its uniqueness comes in its capacity to observe extensive regions of the radio sky and analyze the phenomena present across multiple wavelengths concurrently. The extensive field capabilities are attributed to 13 radio feeds at the focal point of the large dish, in contrast to the singular feed utilized by other radio telescopes, enabling it to see 13 points across a field of view exceeding 1 degree. This enables astronomers to conduct extensive radio surveys more rapidly than usual. The multi-beam facility completed the task in 3 years instead of 30. Another characteristic of the multi-beam facility is its capacity to capture the spectra of radio objects, similar to how astronomers have engaged with visible light for decades. Astronomers can rapidly measure the redshift of galaxies enabling swift calculations of their recession velocity and distance. These two advances generate a swiftly expanding three-dimensional map of galaxies, many of which have not been previously observed. HIPAS is largely a survey of interstellar gas in galaxies situated outside the local group of galaxies. As the study progressed, it became evident that the primary data encompassed substantial information regarding gas in proximity to residents. Data about rapid hydrogen clouds, called high-velocity clouds, HVCs, were particularly interesting. The genesis of HVCs remained enigmatic, prompting the HIPAS team to initiate a PhD research to explore the phenomena. This coincided with the entrance of a new PhD student at Mount Stromlo Observatory, Mary Putman, an assistant professor at the University of Michigan. Her thesis program aimed to elucidate the distribution, origin, and environment of the HVCs. During her efforts, Putman found an unexpected finding. The area surrounding the Magellanic Clouds is a particularly intriguing region for the exploration of neutral hydrogen, and she promptly processed and integrated the data concerning the Magellanic system upon its availability. The outcome was a plethora of new information and a captivating feature advancing ahead of the Magellanic Clouds in the sky. The long-anticipated leading arm of the Magellanic Stream, as forecasted by tidal theory. The preliminary observations indicated that the leading arm is substantial, measuring at least 25 degrees in length, almost 1/4 of the trailing stream identified by Matthewson. The radio brightness is approximately 1/20 of the trailing stream. Thus, if the trailing and leading streams are at the same distance, which cannot be definitively determined, this brightness ratio corresponds to a mass ratio. This does not pose an issue for the tidal theory, however. The leading and following arms would be approximately identical if the tidal interaction was solely two-body. The interaction involves three bodies, the two Magellanic Clouds and the Milky Way, which disrupts the symmetry, as predicted by theory. Numerous tidal theories elucidate the Magellanic Stream. Undoubtedly, all will require modification to accommodate the leading arm. However, our galaxy is implicated in each of them. Utilizing these theories and the currently established space velocity of the Large Magellanic Cloud, one can approximate the mass of the galaxy extending to the Large Magellanic Cloud, around 50 kiloparsecs away. The outcome is approximately 200 billion solar masses, slightly below the typical estimates, yet far greater than the luminous mass, and is heavily contingent upon comprehending the formation of the Magellanic Stream. The Large Magellanic Cloud possesses dark matter, and current rotational analyses indicate a flat rotation curve. Such investigations are intricate due to the disordered and chaotic nature of the system. Our galaxy's black halo envelops it, dramatically affecting its rotation. It is towing its dark matter halo through our galaxy, creating confusion and ambiguity. In summary, it is not the optimal galaxy for research. Unlike many galaxies of comparable luminosity, such interactions do not undermine the investigation of dark matter in small, irregular galaxies. The Milky Way and its surroundings comprise the spiral galaxy, globular clusters, the two Magellanic Clouds, and a collection of satellite dwarf galaxies. This inventory, despite its neatness, is inadequate. If only a small portion of the galaxy consists of luminous stuff, it can no longer serve as a descriptor for the Milky Way. However, as will be seen in the subsequent film, despite the substantial dark matter composition of the Milky Way, it pales in comparison to dwarf galaxies, whose stars merely indicate the presence of vast accumulations of dark matter. Galaxies exhibit a vast array of shapes and dimensions. At one end of the galactic spectrum are massive elliptical galaxies, that predominantly reside at the center of galaxy clusters. These colossal entities include up to 10^12 solar masses and possess overall diameters reaching 200 kiloparsecs. Galaxies such as the Milky Way are far more prevalent among the larger galaxies. Unlike large ellipticals, which constitute approximately 1/5 of all galaxies, spiral galaxies comprise 3/4 of all the luminous galaxies in the universe. Spirals are abundant in gas and dust, the essential components for star formation, whereas ellipticals primarily consist of aged stars and possess minimal material for creating new stars. The remaining 5% consists of irregular galaxies without recognizable shape or structure. A considerable number of galaxies are not included in these statistics. The inclusion of dwarf galaxies alters the count. Certain dwarf irregulars exhibit gas and sporadic star formation, like spiral galaxies. Dwarf ellipticals are predominantly devoid of gas. The population of dwarfs fluctuates based on the environment. They are more prevalent in clusters of galaxies and less so in loose groups. Our local galaxy group is a standard loose assembly with 4 spiral galaxies, no giant ellipticals, 20 dwarf irregular galaxies, and around 17 dwarf ellipticals. Some of the smallest and most prevalent dwarf galaxies are exceedingly faint and challenging to detect, even in deep pictures. They comprise little more than several million stars and a substantial amount of dark matter. The initial indication that dwarf galaxies harbor substantial quantities of dark matter was identified by Mark Aronson, a pioneer in studying dark matter halos within tiny galaxies. In 1987, a tragic accident resulted in the death of Aronson, a renowned astronomer, while he was utilizing the 4-meter telescope at Kitt Peak Observatory. He quantified stellar velocities in some of these diminutive galaxies, which was exceedingly challenging. After measuring merely 6 stars, he observed that the velocity dispersion, specifically the variation in the star's velocities, a fundamental indicator of the pressure maintaining the expansion of galaxies and clusters, was surprisingly substantial. Astronomers regarded this conclusion with skepticism. 6 stars do not yield a significant measure of stellar pressure. Additionally, certain astronomers hypothesized that some stars could be binary systems. Orbital velocity is pertinent when 2 stars revolve around one another, as observed in a binary system. In a survey of stellar motions inside a galaxy, one may observe 2 stars that are part of binary systems. Binaries often comprise a luminous star and a dim, occasionally undetectable, partner. We might obtain a spectrum of the binary system, but only observe the light and lines of the more luminous star, thereby determining its velocity. 2 binary systems inside a galaxy may have identical velocities, but if the luminous star in one binary moves toward the observer, while the brilliant star in the other binary moves away, it generates the illusion of significant velocity disparities. Over time, the spectral lines of both binaries will exhibit oscillation across the spectrum, as each rotating pair of stars alternately approaches and recedes from the observer. However, in a singular survey of the star's movements, significant apparent velocity discrepancies may arise that do not accurately represent the actual motion of the binary systems. This contention persisted for years. However, there are samples of over 100 of these stars in several nearby dwarf galaxies. Despite numerous measurements, astronomers have detected no spectral line fluctuations that would be anticipated if Aronson's stars were binary systems. Astronomers now assert that the stars within these diminutive galaxies exhibit rapid motion, directly suggesting the presence of dark matter. Recently, Ken Freeman has partnered with John Comendi from the University of Texas to elucidate the peculiar characteristics of dwarf galaxies. They not only harbor dark matter, but certain ones possess an exceedingly disproportionate quantity relative to their diminutive size. The two scientists have researched dark matter in dwarf galaxies for an extended period. Several years ago, researchers discovered that the dark matter in these compact galaxies appears exceedingly thick, prompting efforts to correctly ascertain the dark matter. Densities of halos encircling galaxies with varying luminosities. Various individuals assessed halo characteristics using disparate methodologies, necessitating the standardization and purification of the data. This necessitated the reduction of error sources, particularly in developing a reliable method for measuring distances to galaxies, which is consistently challenging. Upon completion, they uncovered significant correlations previously concealed by disorganized data. It was shown that large spiral galaxies exhibit relatively low dark matter densities, whereas smaller galaxies possess progressively higher dark matter densities. Dwarf galaxies, akin to their larger counterparts, exhibit a diverse array of forms. Certain smaller galaxies have a greater quantity of gas than others. If abundant gas is present, they exhibit irregularity and a patchy look in their star-forming areas. If gas is scarce, they seem smooth and are typically referred to as dwarf spheroidal galaxies. Dwarf irregular galaxies exhibit rotation, facilitating the measurement of their halo densities, analogous to the method employed for spiral galaxies. Others, like the dwarf spheroidal satellites of the Milky Way, are mostly sustained by the random motions of their stars. Regardless of the type of dwarf galaxy examined by the two researchers, the outcome remained consistent. Tiny galaxies possess a substantial amount of dark matter, which is highly dense. Indeed, the stars in certain galaxies represent a negligible portion of the entire mass. With the most extreme instances, stars comprise merely 1/100th of the total mass. Studying dwarf galaxies is challenging. The diminished star density in certain smaller galaxies renders their feeble brightness nearly imperceptible in photos. Due to their proximity, astronomers may ascertain the velocities of individual stars, utilizing telescopes like the 3.9-meter Anglo-Australian telescope and the larger 8-meter telescopes located in Chile and Hawaii. Determining the velocity of particular stars necessitates the observation of their respective spectra. Astronomers utilize multi-object spectrographs to simultaneously examine the spectra of numerous stars, as manually targeting each star with a telescope would be inefficient. For larger celestial objects, such as neighboring dwarf galaxies, a network of optical fibers is frequently employed to transmit the light from several stars into a spectrograph. The spectrograph disperses stellar light into a spectrum for analysis. In the initial iterations of these fiber optic systems, one end of each fiber was placed into an aperture in a metal plate secured in the telescope's focal plane. Each aperture was precisely located on the plate, corresponding to the formation of an individual star's image. Although fiber optics significantly enhances the efficiency of astronomical observations at night, which is crucial, given the escalating costs of telescope time, substantial preparatory effort is required to achieve optimal results. To determine the placement of the fiber tips, it is frequently essential to measure a snapshot of the galaxy utilizing a device known as a microdensitometer. Although this process is arduous and prone to errors, precision is essential. If we inaccurately measure the star's position, we will affix the fiber incorrectly on the plate, obstructing its ability to observe anything. Microdensitometers are uncommon precision equipment valued at several $100,000 each. Microdensitometers illuminate a glass photographic plate with the picture of the galaxy being analyzed. The plate is adjusted in 2 dimensions with a precision of 1 millimeter in response to the light. And while the plate functions like a conventional negative, variations in light intensity signify the picture of a star. Upon identification, we transform the positions of the stellar pictures on the plate into right ascension and declination coordinates. These instruments were previously located at Mount Stromlo Observatory and the Sydney offices of the Anglo-Australian Observatory. Regrettably, some 13 years ago, the facility at Mount Stromlo was obliterated by a lightning strike, while the apparatus at the Anglo-Australian Observatory succumbed to obsolescence. Therefore, we must immediately dispatch photographic plates to England for measuring. Australia and England established an agreement to enable this. In exchange for Australia's operation of the UK Schmidt telescope at Siding Spring, the British astronomers would quantify and preserve the photographic plates. In the initial iterations of fibre systems, the locations of the stars were delineated on a circular brass plate, measuring 40 centimetres in diameter and 3 millimetres in thickness. We perforated the plate with minute holes, each denoting the star's position upon its attachment to the telescope. Additionally, larger apertures were drilled at the locations of more luminous guiding stars for fibre bundles, enabling scientists to correctly orient the telescope towards the galaxy. Each smaller aperture was reamed utilizing a jeweler's reamer and equipped with a singular optical fibre. Upon placing the plate within the telescope, we attached the opposing ends of the fibres to a spectrograph. The Anglo-Australian Observatory was the inaugural institution to implement fibre optics in the field of astronomy. The 2DF, 2-degree multi-fibre spectroscopic survey facility, has become a substantial survey device. The 2DF distinguishes itself from the previous instrument by utilizing a robotic system to position the fibers on a reusable plate, rather than manually placing them into a disposable brass plate. Moreover, 2DF performs this function concurrently with the telescope's operation. One plate targets 400 fibers in the telescope's image, while a second plate is arranged with 4 more fibers. A tumbler apparatus, akin to an hourglass, affixes each plate to its external surfaces. After each observation session, the tumbler inverts, allowing the second plate to enter the telescope's focus plane while removing the first plate. As the second set of fibers commences operation, the robot positioner reconfigures the initial setup. All of this occurs at the apex of the 3.9-meter telescope. Developed and built by AAO personnel, one of 2DF's primary functions is to create three-dimensional representations of the universe's structure by mapping redshifts, hence determining distances to galaxies. The success of AAO scientists and engineers led the European Southern Observatory to commission them to construct a fibre positioner for their 8-meter Very Large Telescope in Chile. The fibre positioner is currently operational. Nevertheless, let us revert to the subject of dwarf galaxies. At night, astronomers direct the telescope towards the sky, align the guide stars, and commence their observations. The telescope is focused on the stars of the galaxy throughout the night. Instead of conducting a single prolonged exposure, astronomers typically perform multiple brief, half-hour exposures. This incremental technique enables them to systematically refine the data. A significant issue with CCDs is their susceptibility to cosmic rays, high-energy particles that emanate from all directions in the sky, resulting in information contamination. Such faults are far easier to rectify by amalgamating numerous brief exposures. Despite requiring meticulous planning, the system functions exceptionally effectively. By the conclusion of the evening, each fiber in the system will have facilitated the generation of the spectrum of an individual star. Astronomers can ascertain a star's velocity relative to a known speed reference star by analyzing its spectra. Executing this procedure for all designated stars generates a representation of the velocity distribution, together with the quantity and distribution of mass. Cormendi and Freeman aggregated data of dark matter in 43 galaxies, encompassing the most luminous spirals to the weakest known dwarf galaxies. Their research validated and measured the relationship between a galaxy's luminosity in terms of stars, and the proportional amount of dark matter. Smaller galaxies possess a higher fraction of dark matter within their observable limits. The Milky Way is a substantial galaxy, with over 90% of its mass comprised of dark matter. Yet, in the smallest galaxies with a sparse distribution of stars, dark matter constitutes an even greater proportion of the total mass. An exception to this rule is intermediate brightness elliptical galaxies, which possess around 20% of the luminosity of the Milky Way. Observations of planetary nebulae at considerable distances from their centers indicate that they contain minimal to no dark matter. The reasons for the significant differences among intermediate ellipticals remain unknown. Moreover, although giant galaxies, such as the Milky Way, include greater quantities of dark matter due to their overall mass, they are considerably more concentrated in dwarf galaxies. The faintest dwarf galaxies are scarcely visible, as they contain minimal stars. However, the central dark matter density is approximately 1 solar mass per 30 cubic light-years, which is a 100-fold increase compared to the dark matter density in a giant galaxy, and several times greater than the density of stars and gas in the Milky Way's disk near the Sun. These tenuous galaxies may appear delicate, although they resemble cannonballs more closely. These connections offer novel insights into the influence of dark matter on galaxy formation. Specifically, they aid in comprehending the increasing evidence that the smallest known galaxies, such as the dwarf spheroidal neighbors of the Milky Way, which possess merely 1/100,000th of its light, harbor substantial dark halos. Astronomers were uncertain if such substantial dark halos in these diminutive galaxies are typical, an anomaly, or even a misinterpretation of the observations. The recent observations indicate that it is typical for a dwarf galaxy to possess a high dark matter density, regardless of whether it is a dwarf spheroidal or a gas-rich dwarf irregular galaxy. Why do these seemingly fragile galaxies harbor substantial amounts of dark matter? The explanation resides in the observation that the faintest dwarf galaxies are nearly unaltered relics from the primordial epoch of galaxy formation. A dwarf galaxy represents a fragment of the universe from a distant epoch, potentially when it was merely 1/3000th of its present age and considerably dense. This marks the onset of galaxy fragmentation. Theoretical theories indicate that smaller galaxies emerged prior than larger ones. The majority of the fragments coalesced to form increasingly larger galaxies. Nonetheless, this process resulted in a significant infusion of orbital energy into the nascent, massive galaxy. This resulted in a dispersion of matter, leading to a drop in density as the galaxy expanded. In the Milky Way, the dark matter density is approximately 1/1000th that of a dwarf galaxy. Nevertheless, the massive galaxies did not assimilate all the dwarf galaxies. The small galaxies observed today are those that successfully evaded absorption. The elucidation of the elevated densities of dwarf galaxies posits that whatever dark matter ultimately is, it is almost definitely primordial material from the inception of the universe. This aspect renders the study of dwarf galaxies a captivating area of research. The correlations of dark matter contradict a notion regarding the formation of the majority of dwarf galaxies. Certain astronomers have theorized that dwarf galaxies are formed through the interaction of large galaxies. Gravitational tides extract elongated streams of gas and stars from the parent galaxies during their passage, and small aggregations of gas and stars within these streams can coalesce under gravity, surviving the encounter and resembling miniature galaxies thereafter. This is logical, and certain dwarf galaxies may originate in this manner. But is it the primary method? The region surrounding our galaxy is an appropriate location to search for this type of tidal relic due to the interaction between the Milky Way and the large and small Magellanic Clouds, as mentioned in the preceding film. Distinguishing tidal dwarf galaxies from primordial dwarfs should be straightforward. As big galaxies possess low-density dark halos, causing tidal forces to elongate existing structures. Consequently, tidally formed dwarfs are expected to exhibit reduced dark matter levels compared to their progenitor galaxies. The tiniest dwarfs exhibit significantly greater dark matter densities than the Milky Way or the Magellanic Clouds, indicating that they are genuine galaxies originating from the early universe rather than mere tidal debris. This indicates that the quantity of dwarf galaxies is independent of the restricted number of galaxy collisions since the formation of large galaxies. Dwarf galaxies may possess a greater ratio of luminous matter to dark matter due to the diminished gravitational forces that bind their constituents. The supernova explosions of the initial dwarf galaxies expel greater quantities of gas at the demise of the earliest stars. The explosions minimally impact dark matter, causing tiny galaxies to retain insufficient gas for star formation, which leads to low star counts despite elevated dark matter densities. Astronomers have long recognized that tiny galaxies significantly outnumber giant galaxies, suggesting that many more are still to be discovered. Astronomers have indeed identified dwarf galaxies utilizing the same microdensitometers employed in their preparatory research. By analyzing the positions of stars on existing photographic plates, British astronomers generated contours of star density and saw subtle concentrations of dim stars that were subsequently confirmed to be genuinely related. In other terms, galaxies. The smallest dwarf galaxies possess such a limited number of stars that they are challenging to observe amidst the Milky Way stars and considerably more difficult to identify. Furthermore, the latest discoveries of dwarf galaxies have been facilitated solely by computer analyses of stellar locations. To the human sight, there is no discernible association among the stars. A hierarchy of these satellite galaxies presently exists. In celestial photographs, certain satellite galaxies are discernible to the naked eye, but others remain nearly imperceptible. Before computer analysis, images of the sky in the vicinity of the presumed galaxy reveal no discernible star formations. Nonetheless, the presence of the galaxies is confirmed through measurements of the stars' velocities, indicating their collective motion across space. The extrapolation of the trend indicating an increase in dark matter in progressively smaller galaxies suggests the existence of galaxies with an exceedingly low stellar count, rendering them predominantly composed of dark matter. Dark galaxies are estimated to measure a few hundred light-years in size and possess masses under 10 million solar masses. Unsurprisingly, such items are exceptionally challenging to locate. As previously outlined, one method uses computational searches to identify extremely low star concentrations. Another approach may involve searching for subtle indications of hydrogen gas. The final film characterized the HIPAS survey as a prospective source for such discoveries. The first objective of the multi-beam system was to search for galaxies obscured by the Milky Way. These galaxies are obscured at visible wavelengths due to their light absorption by the gas and dust within our galaxy. Nonetheless, low-frequency radio waves, such as the 21-centimeter radiation, penetrate the Milky Way unobstructed. Consequently, radio telescopes, such as Parkes, can distinctly observe gas-rich, concealed galaxies that remain undetectable by optical observatories. Integrating the multi-beam facility's extensive and multispectral perspective facilitates the rapid and straightforward mapping of gas-rich galaxies' locations. Recent multi-beam survey findings uncovered several galaxies beyond the Milky Way that optical telescopes had overlooked. We now comprehend that these galaxies are situated along sheets and filaments that link to observable objects on either side of the Milky Way. After scientists examined only 2% of the data from the multi-beam survey, a finding emerged: the identification of many dwarf galaxies in the proximate universe. Most dwarfs are dim, uncatalogued dwarf irregulars. identifiable in optical photographs of the sky once their locations are determined. This constitutes a significant discovery. Given the prevalence of dwarf galaxies compared to big galaxies, the former may serve as a more accurate indicator of matter distribution in the universe, encompassing the pervasive dark matter. The presence of dark matter in dwarf galaxies prompts a significant and still unresolved inquiry. Why are globular clusters devoid of dark matter? The rationale behind the dark matter conundrum initiates at the galactic level. Nevertheless, astronomers remain perplexed as to why dark matter is not observable at scales smaller than galaxies. This is a conundrum, as there is no apparent rationale for the absence of dark matter in globular clusters. Large globular clusters possess a mass comparable to the smallest dwarf galaxies, approximately 10 million solar masses. However, they have a diameter roughly 1/10 that of a normal dwarf galaxy. They traverse the dark matter halo of the Milky Way. When gaseous clouds meet, they compress to high densities, resulting in the formation of globular clusters. The formation process, consequently, encompasses solely ordinary matter and excludes dark matter. This is particularly perplexing considering the majority of globular clusters in our galaxy are among the earliest known entities in the universe, forming concurrently with the smallest dwarf galaxies, which are predominantly composed of dark matter. We have now finalized our investigation of dark matter in the universe. We commenced our investigation with Oort's ostensibly erroneous discovery of dark matter in the galaxy's imbalance, proceeded through the extensive dark matter reservoirs of galaxy clusters, and traversed the dark matter-laden dwarf galaxies around the Milky Way. However, one final and undeniably remarkable source of evidence for dark matter must be examined before we can encapsulate the dark matter composition of the universe: gravitational lensing. A fundamental concept of Einstein's general relativity is that space constitutes a physical entity that can be warped by large objects. Space is as concrete as this book, rather than a void traversed by planets and stars. Similar to how one can bend and fold paper, substantial objects can warp the fabric of space, akin to manipulating the paper on which these words are printed. The dimple is a funnel-shaped cavity with inclined edges that flatten as one moves away from the center. Instead of the Earth being tethered to the Sun like a ball on a thread, it traverses the periphery of a gravitational well, akin to a marble on a roulette wheel. Upon learning of general relativity, the British astronomer Arthur Eddington quickly acknowledged its significance and commenced preparations to evaluate its predictions, thinking that was peculiar both then and still. One of its predictions was that, as matter traversed paths of least resistance in spacetime, so too did light. This concept was not particularly novel. Newton's classical theory anticipated that light would be deflected when it traversed a substantial bulk. He regarded light as mass particles, enabling him to compute the quantity of deflected light. How gravity distorts light diverges from Newton's theory. Einstein's concept is sufficiently straightforward to elucidate. Envision yourself aboard a spacecraft isolated from any gravitational forces. You are chained to one wall of the ship to prevent floating, and are holding a torch that illuminates the opposite wall. When the vessel is immobile, the light beam travels in a linear path to the opposite wall of the cabin, impacting the surface at the same elevation from the floor as the flashlight. However, if you activate the rocket engines, the vessel will speed. Despite the rapid velocity of light, its speed is not limitless. This indicates that when a photon departs from the torch, traverses the ship, and impacts the opposing wall, the ship has shifted marginally. The photon will consequently impact the cabin wall near the floor, beneath the elevation where it originated. When observed laterally, the light beam would appear akin to a descending arc of water emanating from a hose. While Einstein could not articulate it precisely, He indicated no distinction between an accelerating vessel in space and a stationary vessel on a planetary surface. Gravity and acceleration are identical phenomena. The remarkable implication is that a gravitational object will distort light similarly to a beam from a flame in an accelerating elevator. Has anyone substantiated such a theory? Eddington recognized that the divergence would be minimal even within a substantial gravitational field, prompting him to select the most massive object, the Sun. He opted to utilize the stars instead of a torch. The theory posits that light from background stars aligned with the Sun would be refracted, altering their perceived location like a celestial mirage. The difference would be minuscule, approximately 2 arc-seconds at the Sun's periphery, comparable to the size of a period at a distance exceeding 100 meters. How can we observe stars in proximity to the Sun? Typically, we extend invitations to them. How can we observe stars in proximity to the Sun? The Moon occludes the Sun in a solar eclipse, rendering the stars visible in the dimmed sky. This would enable Eddington to capture images of the stars adjacent to the Sun and juxtapose their apparent locations with their established fixed placements. Eddington orchestrated 2 excursions to witness the complete solar eclipse of 1919, directing one of the teams to the island of Principe, located off the west coast of Africa. Eddington sent the additional mission to northern Brazil. 2 expeditions were dispatched to northern B. We organized 2 expeditions, expecting that if one team faced cloud cover during the eclipse, the other would experience clear skies. However, both teams encountered favorable weather. The photographs obtained from both teams were analyzed, revealing that the displacement of the star images near the Sun closely aligned with Einstein's predictions. Eddington disseminated his findings to the public in November 1919. The public regarded them as a remarkable validation of Einstein's hypothesis. The public regarded them as a remarkable validation of Einstein's hypothesis. The stars were refracted, and Einstein attained fame. Today's observations produced negligible findings, as the deflections were about equivalent to the measurement errors of the photographic film. Subsequently, researchers have replicated the data with enhanced precision, validating Einstein's renown. We now understand that matter distorts space-time, and light adheres to this distortion. Typically, the curvature is little, resulting in views of stars and planets in the night sky appearing stable and constant. Nonetheless, the deviation becomes apparent when the alignment between a substantial item and a remote light source is adequately proximate. The capacity of substantial objects to modify the trajectories of light rays serves as a crucial instrument in the quest for dark matter: gravitational lensing. If a remote light entity is aligned with an intervening gravitational body, and the appropriate distances are maintained, the image of the more distant entity will be warped and amplified. This resembles how standard reading glasses converge light rays to a focal point. Gravity performs an identical function. If it can deflect individual light beams, it can also deflect bundles of rays, converging them all to a focal point. If one possesses a focus, one obtains an image, an enlarged, albeit distorted, representation of the background object. A gravitational lens is an intervening object that distorts light due to gravitational magnification. Gravitational lensing fundamentally pertains to mass and geometry. The deflection angle of a light beam traversing a distance from a point mass en route to the focus is determined solely by the object's mass and the ray's proximity to the object in space. The deflection is typically little, thus akin to a low-powered spectacle lens possessing an extended focal length. Substantial distances, cosmological distances, are required to generate an image at a specific place utilizing a gravitational lens. The optimal configuration involves equal distances among ourselves, the lens, and the background source. Although this scenario is improbable, a lensing effect would not be observable if we were positioned too close to the lens or the background source. Nonetheless, we should observe a discernible effect provided that the distances are cosmological, 1 billion light-years, or greater between us and the background object, and the ratio between them is not excessive. Typically, the alignment between a remote object and a gravitational lens is imperfect, resulting in a distorted, arc-shaped image of the object as the most discernible outcome. In an ideal scenario, where a distant point mass, ourselves, and the gravitational lens are aligned linearly, the lensing effect would yield a flawless ring centered on the gravitational lens. The radius of the ring is termed the Einstein radius. Notwithstanding the suboptimal alignment of most gravitational lenses, we can measure the Einstein radius of specific arcs. What is the significance of this? The lens's mass can be determined by measuring the Einstein radius through the arc's form and size. The ramifications of dark matter searches are evident, and we will address them shortly. The Einstein radius is frequently referenced in classical literature on gravitational lensing. Is it possible to view the Einstein radius in the sky when expressed in seconds of arc? The MACHO project involves occurrences occurring with background stars, point light sources, and stellar mass gravitational lenses. We quantify these Einstein radii in micro-arc seconds. Therefore, the designation microlensing. Naturally, the arcs are too little to be observed. Nonetheless, this does not invalidate the enhancement of light. MACHO was specifically designed to detect increased light rays reaching the telescope due to lensing, resulting in brighter images. The Einstein radius for clusters may range from several arcseconds to 20 arcseconds, due to the significant distances and substantial masses of the clusters. As previously stated, for a specific configuration of the light source, lens, and observer, the observed lensing in the sky solely depends on the mass of the lensing object, assuming it is sufficiently compact. The larger the object, the greater the gravitational distortion observed. The intriguing element for dark matter researchers is that the degree of deviation is only dependent on mass, allowing for determining a gravitational lens's mass by measuring the deviation amount. The elegance of this method resides in its capacity to ascertain mass without reliance on assumptions or theories. There is no uncertainty regarding this matter. General relativity precisely predicts the degree of deflection corresponding to a specific mass. One must not undervalue the significance of understanding the geometry, namely the distances between the source and lens, as well as the observer and lens. Any mass can distort light and hence function as a gravitational lens. The sole inquiry is whether we can detect the curvature. This is the domain of astronomy. Nearby objects, like the Sun, induce a minor, detectable deflection, whereas more distant stars within our galaxy can distort the light from stars behind them. The pivotal element in all these instances is that the background light source and the foreground object are aligned, or near, our line of sight. Our perspective of the galaxy's stars is hindered by a curtain of stars, enabling us to observe more remote background entities. Moreover, the entire galaxy is in motion, resulting in the continuous movement of its constituent stars across the sky, albeit at a relatively slow pace, as observed from Earth. Given the multitude of stars traversing the field of vision, some will likely align with a more distant object. Consider two clusters of galaxies aligning in more remote instances, resulting in a distinct scenario. Indeed, as articulated in Film 3, both Einstein and Eddington deemed the likelihood exceedingly improbable, concluding that although it was an intriguing concept, it had negligible practical utility. However, in 1936, Einstein did publish the notion of gravitational lensing. Zwicky postulated that gravitational lensing would be observable if a galaxy aligned with the line of sight of a more distant object, such as a quasar. Due to their luminosity and typical visibility at far larger distances than conventional galaxies, quasars function as brilliant background light sources. In Film 3, Zwicky expanded on this concept by asserting that galaxy gravitational lensing was feasible and would serve as a potent method for examining the quantity and distribution of dark matter within the foreground cluster. This occurs when a nearby galaxy or cluster exerts pressure on a distant quasar. Zwicky was accurate, even though the initial detection of a gravitational lens transpired 60 years after Eddington's renowned eclipse experiment. Furthermore, gravitational lensing is an optimal method for examining the masses of galaxy clusters. Galaxy clusters represent some of the most densely concentrated aggregations of matter in the universe, confined to very compact spatial regions. They are diminutive relative to the distances separating us from background light sources, indicating their complete adherence to the gravitational lensing parameters previously mentioned. The universe is abundant in galaxies, especially those that are distant. Envision a cone surrounding the cluster, with us at the apex. Beyond the cluster, this cone encompasses a vast expanse of space, augmenting the likelihood of encountering a galaxy or multiple galaxies that may be lensed. As we explore space farther, we observe a growing multitude of galaxies, offering an abundant supply of background light sources. Astronomers often detect strong lensing in affluent galaxy clusters, producing numerous pictures of a background object. Magnification will enhance one or more photos, rendering them brighter than usual, while certain multiple images may appear dimmer. Strong lensing presents a viable resolution to a significant issue in cosmology: the ascertainment of the contentious Hubble constant, as outlined in Film 2. Determining the Hubble constant has posed a significant issue for astronomers throughout the past century. Recall that Hubble demonstrated that the greater the distance of a galaxy, the more rapid its recession. This occurs because each galaxy is moving away from every other galaxy. When observing two galaxies, one positioned behind the other, the nearer galaxy appears to be receding from our vantage point. The remote galaxy will retreat at double the speed of the closer one due to its motion away from us. It functions reciprocally. The denizens of either of the other two galaxies will observe exactly the same phenomenon. All galaxies in the universe are receding from one another as a natural result of cosmic expansion. In 1929, Hubble demonstrated that this phenomenon was occurring and calculated an initial rate of 200 km/s per megaparsec. Galaxies withdrew from us at an additional 200 km/s for each megaparsec of increased distance. Nevertheless, he miscalculated the distances to the galaxies, resulting in a significant decline in estimates of the Hubble constant once their actual distances were determined. The instrument named in his honor, the Hubble Space Instrument, has established the number at a widely recognized 72 kilometers MPC. Does gravitational lensing provide evidence for this figure? Previously, we noted that a variable influencing gravitational lensing is the distance to the lensing cluster, which is contingent upon the velocity at which the cluster is receding from us. The Hubble constant is the factor that connects these two significant numbers. Diverse light rays generate numerous images, each traversing a distinct path from the source to us. Each path possesses a distinct length. Thus, when the background source is a quasar that fluctuates in luminosity over months to a year, the variation in brightness of the different lensed images offers a method for assessing the relative distances or path lengths between the quasar and the observer. The phase difference, defined as the disparity in arrival time at the peak or trough brightness of the two pictures, is contingent upon the Hubble constant. It facilitates the measurement of the Hubble constant, rendering lensing an independent method for quantifying this crucial value. The essential element is comprehending the lens thoroughly, which relies on its modeling. None of the systems examined thus far possess a simple point mass, complicating matters somewhat. The findings indicate the Hubble constant is measured at a low value of 50-60 km/MPC. Nonetheless, they possess significant uncertainty regarding the characteristics of the lens. Nevertheless, it presents an intriguing approach to the issue, and in a realm where each technique has its limitations, a novel autonomous method is highly appreciated. Although more challenging to identify, weak lensing occurs more frequently than strong lensing. This does not generate numerous photos, but instead distorts the image of the background light source. Weak lensing alters the shape of the background object. This phenomenon is not readily apparent and can only be statistically discerned by analyzing the forms of numerous photographs in a specific direction in the sky and identifying distortions in a uniform orientation. This distortion would be orthogonal to the line connecting the object's image and the center of mass, resulting in the distortion. Meticulous analysis of photos, predominantly acquired with the Hubble Space Telescope, supplemented by high-quality ground-based data, has detected this phenomenon. Resolution is crucial for identifying these minute image aberrations. Strong lensing is far more prominent, and historically the inaugural strong lens system identified was the double quasar 0957 Plough561. Astronomers had been searching for distinctly blue quasars, especially in the UV spectrum. A team directed by Dennis Walsh captured an optical photograph of the quasar 0957 Plough561 and discovered two adjacent star-like images, separated by around 5.7 arc seconds. For anyone acquainted with the telescopic site of the double star, Alpha Centauri constitutes roughly 1/3 of the distance separating the components. Upon acquiring a spectra of one of these objects, its significant redshift identified it as a quasar. They commendably conducted a spectral analysis of the second item, as it was likely merely a foreground star within our galaxy. The two objects possess identical spectra and have the same redshift. The proximity of two quasars may be coincidental, as twin quasars do occur. Confirmatory evidence emerged following long-term investigations that demonstrated the two photos exhibited comparable brightness variations, with one image's variation occurring 420 days later than the other. The photos needed to depict a singular quasar, which must have been significantly lensed by a foreground entity, likely a galaxy or a cluster of galaxies. This is an exceptional instance, mostly due to the rarity of quasars being lensed in this manner, with a discovery rate of approximately 1 per year. Conversely, robust lensing of galaxy clusters is significantly more prevalent, with Abell 2218 as one of the most exemplary instances. This affluent galaxy cluster, situated around 3 billion light-years away, gained prominence when it was photographed by the Hubble Space Telescope in 1994. The image is derived from a study conducted by a consortium of astronomers from 4 universities: Warwick Couch, University of New South Wales; Richard Ellis and Jean-Paul Kniebe, Cambridge University; Ian Smale, Carnegie Institution of Washington; and Ray Sharples, University of Durham. It is now one of the most exemplary instances of strong gravitational lensing ever identified. The utilization of the Hubble Space Telescope to examine remote clusters was driven not by gravitational lensing, but by the analysis of galaxy morphology, their shapes and structures. The galaxy cluster was recognized to be experiencing significant development. The individual galaxies exhibited a significantly bluer hue and were undergoing star creation. The astronomers endeavored to get optimal photographs from the ground to ascertain the structural characteristics of distant galaxies, but the galaxies' considerable distance and the diminutive size of their images rendered morphological details frustratingly elusive. The decision was made that the sole method to get a definitive understanding of galaxy morphology was to utilize a space-based observatory, unencumbered by the distorting influences of the Earth's atmosphere, the Hubble Space Observatory. With a resolution an order of magnitude greater than that achievable on Earth, it would facilitate a novel domain of research in elucidating the anatomy of far galaxies. It has been determined that intense lensing is frequently observed in dense clusters of galaxies. One appeared in the initial cluster, which was seen by astronomers using the Hubble Space Telescope. The image was shaped like an L, with at least two images in the center. The asymmetrical duo of images that were mirror reflections of one another indicated the presence of a gravitational lens. It soon became apparent to the scientists that they could concurrently examine the morphology of remote cluster galaxies and extensively analyze gravitational lensing. The Hubble Space Telescope can identify gravitational lenses, quantify their mass, and investigate dark matter. Before the repairs of the Hubble Space Telescope, scientists captured the initial photos in 1992. Despite the telescope's compromised condition, its potential for this type of work was extraordinary, and it was evident that it would have a promising future following repairs. The team's investment of time in seeing multiple high redshift clusters provided them a competitive edge over the broader astronomical community. The decision was made to optimize future observations for studying galaxy morphology and maximizing the benefits of gravitational lensing. Abell 2218 is recognized as a powerful gravitational lens based on ground-based imagery. The immense gravitational field has warped and amplified the images of background galaxies, located 3 to 4 times farther away, into multiple slender and dim arcs. It was a conspicuous object for space investigation, hence designating it as one of the targets. The photograph of Abell 2218 was captured with the Wide Field Planetary Camera 2 in September 1994. The astronomers were astounded upon receiving the image, unaware of its impending magnificence. It displays not only the foreground cluster of galaxies, but also a remarkable array of brilliant arcs, distorted pictures of distant galaxies, encircling the galaxies of the foreground cluster. It has since emerged as a benchmark, a quintessential example of a gravitationally lensed cluster. After the Abell 2218 image, the team continued examining galaxy morphology and enlisted specialists in lensing analysis. The lensing analysis is complex because galaxy clusters are not merely point masses, but broad mass distributions. Ellis and Smale conducted ground-based surveys to investigate potential evidence of arcs indicative of significant lensing, and they identified a commendable sample of clusters exhibiting lensing evidence. Jean-Paul Canaib, a French postdoctoral researcher at Cambridge, was responsible for modeling Abell 2218 and analyzing the lensed images of the cluster. Before joining the team, Canaib had dedicated his entire research career to this work, equipping him well for the task. He possessed the software on a computer to examine the clusters, making him a highly suitable candidate for involvement. The ensuing examination of Abell 2218 yielded 2 outcomes. Initially, ascertaining the bulk distribution of the cluster necessitates some trial and error. We first construct a model of the lens based on factors like the light distribution observed in the photos. The luminous matter is an initial indicator of the potential distribution of the underlying dark matter. Subsequently, a computer mimics the behavior of various light rays emanating from diverse background objects as they traverse the cluster, a technique known as ray tracing. We adjust the model until it accurately reproduces the original image. We can derive substantial information from the Hubble Space Telescope photos, enabling us to impose limitations on the model. We implement additional tweaks until the model accurately reproduces the image. This method allows for a precise definition of the properties of the gravitational lens. The Hubble Space Telescope image of Abell 2218 is an advantageous addition to this research, as it captures a rare phenomenon: the manifestation of several images of distinct galaxies. 7 unexpected multiple pictures were discovered. Strong lensing provided an opportunity to measure the galaxy cluster's mass through each batch of multiple photos. This phenomenon occurred because each image possessed a distinct impact parameter: the distance between the line of sight traversing the lens, the background object, and the image. This distance fluctuates based on the mass of the intervening object. As the light rays from each background galaxy follow divergent trajectories through the foreground cluster, each provides an independent assessment of the foreground cluster's mass. Consequently, it becomes feasible to ascertain the mass between the image's apparent position and the actual line of sight. The presence of multiple images situated variably from the foreground cluster's center is essential. With articles observable at different locations within the image, it becomes possible to measure the foreground cluster's mass at varying distances from the center. The second outcome from the image involved ascertaining the distance to the background galaxies. The lensing equations are contingent upon the overall geometry: the distances between the source, the lens, and the observer. Redshift observations can readily ascertain the distance to the lensing cluster. However, the distance from the lensing cluster to the background source remains unknown. Nevertheless, once the lens characteristics are established through computer simulations, as previously described, it becomes feasible to compute the distance to the background galaxies. By knowing the distance of the background galaxies from the lens, and consequently from ourselves, one can determine the duration since the light departed from the background galaxies, the look-back time. This facilitates an understanding of the properties of galaxies during that epoch. Following the acquisition of this renowned image, astronomers have estimated the distances of 120 objects, enabling the assessment of 50 times dimmer galaxies than those detectable by terrestrial telescopes. Consequently, a gravitational lens can be a colossal telescope to examine entities that otherwise elude even the most powerful ground-based instruments. In the absence of gravitational lenses, remote galaxy clusters would be scarcely perceptible. However, lenses like Abell 2218 enhance their visibility by factors ranging from 10 to 50. The distant galaxies beyond Abell 2218 are situated at a redshift of 1 to 2, indicating their existence when the universe was less than half its current age. The discovery of Abell 2218 enhanced the investigation of dark matter and initiated a substantial field of research, leading to the imaging of numerous rich galaxy clusters with the Hubble Space Telescope. Gravitational lensing offers compelling evidence that dark matter comprises most of these clusters. Research utilizing gravitational lensing has revealed that 90% of the clusters are predominantly dark. Although variations exist among clusters, luminous matter consistently accounts for less than 15% of the total cluster mass. Lensing clusters exhibit dark matter akin to galaxies, though it may be more densely concentrated in the center compared to luminous matter. Gravitational lensing serves as an effective method for investigating dark matter. It involves no intricate physics or extraneous variables, allowing for a direct assessment of the foreground cluster's mass, encompassing both luminous and dark components. Gravitational lensing images also directly represent the luminous matter within the foreground cluster. By juxtaposing the luminous mass with the lensing mass, we can ascertain the mass-luminosity ratio of the cluster and quantify the dark matter present. While clusters are not mere point masses, but rather complex systems comprising hundreds of galaxies within a dark matter halo, certain assumptions regarding the distribution of dark matter must be made. The theoretical framework has been sufficiently refined to yield highly accurate measurements.